Hi everyone, welcome back to the channel. My name is Martin Yanev, a professional software engineer and a computer science professor at Fitchburg State University. In the next few hours, I will show you how to program in Rust, and more specifically, we're going to learn asynchronous programming. You'll gain hands-on experience on async and await features and popular async runtimes like Tokyo. This course is made for beginners, but it emphasizes on high-performance applications. You can expect to gain a lot of valuable skills in Rust after you complete it. As always, the code will be linked in the description. Make sure to like this video and especially to subscribe to this channel if you want to watch more free courses like this one. Now let's jump straight to the course.
Asynchronous programming is one of those topics many programmers find confusing. Let's demystify it together by diving into the world of concurrency. In a nutshell, concurrency is all about dealing with lots of things at once. It allows you to run multiple processes or threads simultaneously, improving the efficiency and performance of your applications. This means your programs can become more responsive and capable of handling numerous tasks at the same time, a bit like multitasking but for your code. Next, we will write the following code to demonstrate how to use the threading module in Python for managing concurrency. In this example, we begin by importing the necessary libraries: threading for creating threads and time for simulating delays. We define a function named task, which takes a name and a duration as parameters. Inside this function, we print a message indicating that the task has started, then pause execution for the specified duration using timesleep, and finally print another message once the task is completed. Now let's see how we can implement this by creating two separate threads, thread 1 and thread 2, each responsible for executing the task function with different durations. We initiate both threads by calling their start method, which allows them to run concurrently. To ensure that the main program waits for both threads to finish their execution, we use the join method on each thread. This setup showcases the behavior of concurrent tasks in Python, as both tasks will start nearly simultaneously, enhancing the efficiency and responsiveness of the program. Now let's take a look at an implementation of asynchronous programming using the Asyncio library in Python. In this example, we define an asynchronous function called fetchData. This function simulates the process of fetching data from an API by printing a message and then pausing for a specified duration using await Asyncio sleep. This pause allows the event loop to perform other tasks, demonstrating how asynchronous operations can proceed without blocking the execution of other functions. Next, we introduce the main function, which is responsible for coordinating our asynchronous tasks. By using Asyncio gather, we can initiate multiple fetchData calls concurrently, specifically for API 1 and API 2, where each call is provided with a random duration between 1 and 3 seconds. This means that both tasks can execute at the same time, resulting in an efficient and responsive program, particularly valuable when dealing with I/O-bound operations such as network requests. Finally, we use Asyncio run main to kick off our asynchronous program. This approach allows us to harness the power of concurrency in Python effortlessly, making our code faster and more efficient. Now let's explore how we can leverage the multiprocessing library in Python to handle CPU-bound tasks efficiently. In our example, we define a function called calculateSquare, which takes a number as input, computes its square, and prints the result. To simulate a delay and mimic the processing time, we include a short sleep. Next, we check if the script is being run as the main program, which is important to prevent unintended execution when importing. We create a list of numbers that we want to process. For each number in this list, we instantiate a new process object from the multiprocessing module targeting our calculateSquare function. We also pass the current number as an argument. By starting each process, they run concurrently, allowing us to exploit multiple CPU cores. To ensure that the program waits for all processes to finish executing before continuing, we utilize the join method for each process. Finally, we print a completion message confirming that all processes have finished their tasks. This approach demonstrates how effective multiprocessing can be in managing separate tasks simultaneously, leading to faster execution times in CPU-intensive applications. Now let's delve into how we can manage shared resources safely when using concurrency with Python's threading module. In this example, we define a function called incrementSharedCounter, which takes a list counter as an argument. This function simulates an operation that increments the value of counter multiple times with a brief pause in between to mimic processing time. To prevent data corruption due to simultaneous access by multiple threads, we employ a lock mechanism. We first create a lock object before defining our function. Inside the loop, we use the withLock statement, which effectively acquires the lock before modifying the shared counter and automatically releases it once the block is exited. This ensures that no other thread can access the counter while one thread is incrementing it, preventing race conditions. Next, we create two threads that execute this function concurrently, both aiming to modify the same counter. After starting the threads, we call join on each one, which makes the main program wait until both threads have finished executing. Lastly, we print the final value of the shared counter, demonstrating how locks help maintain the accuracy of shared data in a multi-threaded environment. As we wrap up this introduction to concurrency, it's crucial to highlight the importance of choosing the right concurrency model based on your application's needs. For example, if your program is I/O bound, asynchronous programming with Asyncio can make it significantly more efficient. Conversely, if your program is CPU bound, using multiprocessing to harness multiple cores can lead to dramatic performance improvements. Lastly, remember that learning about concurrency takes practice. Gathering knowledge from this introduction will set a strong foundation, but the best way to master concurrency is through coding and experimentation. The next time you encounter a seemingly long task in your code, consider how you could break it into concurrent operations. We've made quite a journey through the world of concurrency today, and I hope you've gained valuable insights into these concepts. It can be a bit overwhelming, but remember, concurrency is just about handling multiple tasks effectively. Meandering through threads, processes, and async functions may seem tricky, but practice is where the magic happens. Keep coding and don't let confusion hold you back. Embrace the excitement of writing efficient, concurrent code. By understanding how and when to use concurrency, you can create responsive applications that enhance user experience and maximize resource utilization. Let's go forth and apply these newly acquired skills. Happy coding. In today's lesson, we're going to explore the fascinating worlds of parallelism and concurrency. These concepts are crucial in modern programming and allow our applications to run efficiently and perform multiple tasks at once. So far, we learned that asynchronous programming and concurrency allow programs to handle multiple tasks simultaneously, enhancing efficiency and responsiveness. We explored how threading and the threading module enable concurrent task execution, followed by an introduction to asynchronous programming using Asyncio for I/O-bound operations. We also covered the use of processes through the multiprocessing library for CPU-bound tasks, and highlighted the importance of managing shared resources to avoid issues like race conditions. Finally, we emphasized the significance of selecting the right concurrency model based on the application's requirements and the value of practice in mastering these concepts. Now we will talk about parallelism and concurrency, how they differ, and how they complement each other in delivering effective solutions. Let's kick things off with a fundamental distinction. Concurrency is about doing many things at once, while parallelism is about doing many things simultaneously. Imagine you're in a kitchen preparing dinner. If you chop vegetables while boiling water, you're being concurrent because you're overlapping tasks. But if you had a helper who's boiling the water while you chop, that's parallelism, as both tasks are occurring at the exact same time, leveraging multiple resources. To understand how this translates into coding, we'll look at an example using Python's concurrent futures, which abstracts away some of the complexities of thread and process management. Now let's see how we can implement a concurrent approach to cooking multiple items simultaneously using Python's concurrent futures module. In the provided code, we start by defining a function called cookItem, which simulates the cooking process of a dish for a specified amount of time. Inside this function, we print a message indicating that the cooking has started, pause the execution for the given duration using timesleep, and then print another message when the item is ready. Next, the preparedEnv function is where the real concurrency comes into play. We create a list of items, each paired with its respective cooking duration. Using a thread pool executor, we can define a pool of concurrent threads with a maximum of 3 workers in this case. For each dish in our list, we submit the cookItem function to the executor, which schedules the tasks to run concurrently. This approach allows us to efficiently manage cooking times, reflecting a real kitchen scenario where multiple dishes can be prepared simultaneously without getting in each other's way. Finally, when the script is executed, it initiates the dinner preparation, showcasing how concurrency enhances efficiency in task management. Next, we will implement an example using the multiprocessing module to leverage parallelism in Python. The first step involves importing the multiprocessing library, which provides the necessary functionalities to create and manage multiple processes. Now let's look at the calculate square function, which takes a single number as input and returns its square. This function serves as the individual task that each process will execute. In the main block, we define a list of numbers that we wish to process. Here we have 5 numbers, 1 through 5. Next, we create a pool of processes using multiprocessing pool, where we specify that we want to use 3 processes. This allows us to run these processes concurrently on different CPU cores. By calling pool.map, we distribute our list of numbers across the available processes, with each process calculating the square of its assigned number in parallel. Finally, the results are collected into a list, which we print to display the squares of the given numbers. This approach drastically reduces the overall computation time compared to a sequential execution, showcasing the power of parallel processing. Let's take a moment to address efficiency. Concurrency can improve responsiveness, especially in I/O-bound applications, by efficiently managing waiting times. Even though tasks don't necessarily run simultaneously, they make progress together. On the other hand, parallelism can significantly reduce execution time for computationally intensive operations where tasks can run at the same time across multiple processes. That said, they can indeed work together. You can have a concurrent application that performs multiple I/O-bound tasks while simultaneously offloading CPU tasks to various processes. The realities of concurrency and parallelism extend beyond the execution of tasks. They also involve proper management of resources and addressing challenges like race conditions. Picture this: you and a friend are sharing a car. If both of you reach for the steering wheel at the same time, you might run into trouble. That's where synchronization comes in. Just as in driving, where you need to communicate and manage turns in code, we need mechanisms like locks and semaphores to control access to shared resources. Here's an example of how we can use locks in a concurrent program. Now let's take a look at how we can implement a thread-safe counter using Python's threading module. In this code, we start by initializing a global variable called shared counter, which will be incremented by multiple threads. To ensure that modifications to this shared resource are safe from interference, we create a lock using threading lock. This lock will help us control access to the counter, preventing race conditions. Next, we define a function named incrementCounter, which contains a loop that runs 1,000,000 iterations. Inside this loop, we use the lock with a with statement to ensure that only one thread can increment the counter at a time. By enclosing the increment operation within the lock, any thread that attempts to modify the counter will have to wait until the lock is released, which leads to predictable and accurate results. We then create and start 2 threads that execute the incrementCounter function. After starting the threads, we wait for both to finish their execution using the join method. Finally, we print the final value of the counter, which should be precisely 2,000,000 if everything has worked correctly, illustrating the importance of synchronization in concurrent programming. While concurrency and parallelism enhance performance, they can also introduce complexity, especially around state management and sharing resources between threads and processes. Ensuring your application behaves predictably requires a solid understanding of how tasks interact with shared state. Furthermore, the choice between concurrency and parallelism depends largely on the type of application you're developing, whether it leans toward I/O-bound or CPU-bound tasks. If your application predominantly waits for the user or responds to input, concurrency is the way to go. However, if you're performing heavy computations, parallelism will be your ally. For aspiring programmers, grasping these concepts provides a significant advantage. Understanding when to apply concurrency versus parallelism can help you build more efficient and responsive applications that scale as your user base grows. Getting comfortable with these concepts means diving in and experimenting. As we wrap up this exploration of parallelism and concurrency, let's quickly recap what we've learned today. We distinguished between concurrency, taking turns doing things, and parallelism, which is executing tasks simultaneously. We walked through simple examples of concurrency using threads and parallelism using processes. Moreover, we addressed the complexity of managing shared resources and how synchronization makes it possible to prevent race conditions, ensuring the integrity of shared data. As you move forward, remember to choose the right model based on your task requirements and continue to practice. Your coding skills will benefit immensely from it. So there you have it, folks. Parallelism and concurrency may seem daunting, but they are fundamental tools in the programmer's toolkit. With a pinch of practice and experimentation, you too can harness the power of these concepts to build robust and effective applications. Happy coding! The operating system, OS, stands at the heart of everything we do as programmers, playing a crucial role in managing system resources and facilitating communication between software and hardware. Today, we are going to explore the vital role of the operating system in asynchronous programming, delving into how it enables our applications to handle multiple tasks efficiently without getting bogged down in the details. So far, we learned that concurrency and parallelism are essential for efficient programming, allowing applications to handle multiple tasks at once. Now we will cover how the OS orchestrates asynchronous programming, making these efficiencies possible. As we dive in, it's important to recognize that asynchronous programming allows a program to initiate a task and continue executing other tasks without waiting for the initiated task to complete. This non-blocking execution is particularly beneficial in I/O-bound applications, such as web servers or GUI applications, where the program must remain responsive while waiting for external resources like network responses or file reads. The operating system plays a pivotal role in this process by managing how tasks are executed and how resources are allocated. Now let's take a look at an example of how to implement an event loop with asynchronous tasks in Python using the Asyncio library. In this code, we define two asynchronous functions, task1 and task2, which simulate I/O-bound operations. Each task begins by printing a message indicating that it has started and then uses await Asyncio sleep to mimic a delay, representing the time taken for an I/O operation. This allows other tasks to run concurrently while these tasks are awaiting completion. Next, we create a main function that serves to initiate these tasks. It begins by printing a message signaling that tasks are starting and then calls Asyncio gather to execute task 1 and task 2 concurrently. This function allows for waiting on multiple async calls simultaneously, showcasing how the event loop efficiently manages the execution flow. Finally, the asynchronous operations are kicked off by checking if our script is being run directly, at which point Asyncio run main is invoked. This initializes the event loop and runs our main function, ensuring that our program can handle multiple I/O tasks without blocking, thus maintaining responsiveness throughout its execution. Now let's implement a task scheduler that prioritizes the execution of asynchronous tasks. We begin by creating a task scheduler class that utilizes Python's queue, priority queue. This allows us to manage tasks according to their priority levels. The constructor of this class initializes an empty priority queue where tasks will be stored. Next, we define the addTask method, which accepts a priority and a task function. This method places the task into the priority queue, ensuring that it can be retrieved based on its priority. Higher priority tasks will be executed first when we run the scheduler. The run method is crucial as it continuously checks if there are tasks in the queue. If tasks are present, it retrieves and executes them in order of their priority, printing a message indicating which task is currently running. Each task is an asynchronous function, which allows for non-blocking execution even if one task is waiting or paused. To illustrate how the scheduler operates, we define an example task function called example_task, which simulates a task that takes a certain duration to complete. Finally, in the main block, we create a scheduler instance, add multiple tasks with different priorities, and execute them using the Asyncio event loop. This demonstrates the effective management and execution of tasks based on priority, showcasing the operating system's role in resource allocation. Now let's implement a simple asynchronous I/O operation using the AFiles library, which enables non-blocking file operations in Python. We begin by defining an asynchronous function named readFile, which takes the path of the file to be read as its parameter. Within this function, we utilize AFiles open to asynchronously open the specified file in read mode, ensuring that this operation does not block our program's execution. By using the async with statement, we manage the file's context, which guarantees that the file is properly closed after we are done with it. Next, we await the reading of the file's contents using await file read. This allows our program to yield control back to the event loop while waiting for the file I/O operation to complete, thus maintaining responsiveness. As soon as the contents are read, we print them to the console. Finally, we define the main function which serves as the entry point for our asynchronous operation, calling read file with a specific file path. By running asyncio run main, we execute our asynchronous code, showcasing how simple it is to handle file I/O operations non-blockingly in Python. Now let's see how we can implement error handling in our asynchronous code. In this example, we define an asynchronous function called risky task, which simulates a task that may fail by raising a value error after a brief pause. This pause is achieved using the await asyncio sleep1 call, which allows the function to wait for 1 second before executing the error. Next, in the main function, we employ a try block to await the execution of risky task. This structure enables us to catch any errors that occur within the asynchronous code. If the value error is raised, the control shifts to the accept block, where we handle the error gracefully by printing a message that includes the error details. This technique prevents the entire application from crashing due to unexpected errors, showcasing robust error management in an asynchronous context. Finally, by running the main function with asyncio run, we ensure that our asynchronous tasks are executed within the event loop provided by the operating system. This allows us to manage errors effectively while still maintaining responsiveness in our application. Now let's see how we can perform an asynchronous HTTP request using the epoll library. This example highlights the power of the operating system in managing network I/O through efficient, non-blocking calls. We start by defining an asynchronous function called fetchData, which takes a URL as an argument. Inside this function, we create an epoll client session context, allowing us to manage HTTP requests more effectively. Each request is made within an async with statement, ensuring that resources are properly released once the response is received. Next, we use the session's get method to send a request to the provided URL. The key here is the await keyword, which pauses the function's execution until the data is ready to be processed. After fetching the response, we read the text content and print it out, illustrating how seamless it can be to handle data asynchronously. In the main function, we specify the URL to retrieve data from and call fetchData using await. Finally, the program is executed using asyncio run main, showcasing how the OS efficiently ties together asynchronous programming, networking, and high-level APIs to deliver a responsive application experience. Finally, we should reflect on the relationship between the operating system and the developer. While the OS abstracts the complex details of managing tasks and resources, it is essential to understand these underlying processes to harness the full capabilities of asynchronous programming. Leaving the management of tasks exclusively in the hands of the OS can lead to unexpected bottlenecks and performance issues. By being aware of how the OS operates and the tools it provides, you can optimize your asynchronous code for better performance. For instance, understanding how many concurrent connections your OS can handle or recognizing the need for optimal memory usage while working with large datasets will lead to more resilient, high-performance applications. As you continue your journey into asynchronous programming, remember that the operating system is your ally. It manages the underpinnings of task execution, event loops, resource allocation, and I/O operations, allowing you to write more efficient and responsive applications. Stay curious, experiment with your asynchronous code, and utilize the power of your OS to create fantastic applications that can handle multiple tasks seamlessly. In conclusion, the operating system serves as the backbone of asynchronous programming, facilitating critical functions that allow applications to run smoothly and efficiently. From managing event loops and executing tasks based on priority to handling non-blocking I/O operations and ensuring robust error management, the OS plays a central role in how we develop and structure our programs. Understanding its role empowers you as a developer, enabling you to craft responsive, high-performing applications in today's fast-paced computing environment. Keep these concepts in mind as you dive deeper into the realms of asynchronous programming, and you'll surely see the benefits in your creations. Happy coding! Let's dive straight into the fascinating world of concurrency. It's a topic that, once mastered, opens doors to building efficient and responsive applications. So far, we've learned that the operating system plays a critical role in managing resources and facilitating communication between software and hardware, particularly focusing on asynchronous programming. We've uncovered how the OS deploys event loops to process tasks concurrently, ensuring our applications remain responsive during those inevitable waiting periods in I/O operations. Now, we will talk about concurrency and how it empowers developers to think differently about resource management, task execution, and application design. Now let's implement a simple TCP server that demonstrates concurrency using Python's threading module. The server begins by importing the necessary libraries: threading for managing multiple threads, time for simulating processing delays, and socket for network communication. In the handle client function, we first accept incoming requests from clients and print a message with the received data. To simulate processing time, we include a time delay, which stands in for potential I/O operations you might encounter in a real-world application, such as database queries. Once processing is complete, we send a simple HTTP response back to the client and close the connection. Next, we define the start server function, where the server socket is created and bound to port 9999. The server listens for incoming connections, and when a new client connects, it accepts the connection and launches a new thread, invoking handle client to manage that client's request. This allows our server to handle multiple requests concurrently, significantly enhancing its responsiveness and efficiency. The threading model ensures that each client is processed in parallel, which is vital for maintaining high performance in modern applications. Now let's implement a more robust concurrent server that safely manages access to a shared resource. In this code, we introduce a global request counter variable to keep track of the number of requests handled by the server, which is a vital part of monitoring the server's performance. To ensure that our counter is updated safely when multiple threads handle client requests simultaneously, we use a counter lock. This lock serves as a synchronization mechanism, allowing only one thread at a time to modify the request counter. Inside the handle client function, the request is received from the client, and we enter a context manager using with counterlock. This ensures that once a thread has entered the block to update the request counter, other threads are blocked from entering until it is completely done. After updating, we proceed to simulate processing time with a sleep function before sending a response back to the client. For the server's main functionality, the start server function sets up a TCP socket, binds it to the specified address and port, and listens for incoming connections. Each time a connection is accepted, a new thread is initiated to handle that client, allowing the server to manage multiple requests concurrently without losing track of how many requests have been processed. Now let's see how we can implement an asynchronous operation in JavaScript using promises and the async await syntax. In this example, we define a function named requestHandler that returns a promise. This promise simulates an asynchronous operation by using setTimeout, which delays the resolution of the promise by 1 second. When the promise resolves, it logs a message indicating that the request for the specified URL has been handled and returns a string response. Next, we create an async function called handleRequests. Inside this function, we first log a message indicating that we are handling the requests. We then make 2 asynchronous calls to requestHandler, awaiting the results of each. The use of await here ensures that while one request is being processed, the JavaScript engine can continue executing other operations, thus effectively demonstrating the concurrency model of JavaScript. After both promises resolve, we log the responses to the console, showcasing how asynchronous programming allows for efficient handling of multiple tasks without blocking the execution flow. Next, let's explore another critical concept within concurrency: cooperative versus preemptive multitasking. In cooperative multitasking, tasks voluntarily yield control before running another task, while preemptive multitasking allows the operating system to forcibly switch tasks, often leading to more efficient CPU usage. Understanding how your programming environment manages these strategies is essential for performance optimization and avoiding pitfalls like starvation, where a task never gets the opportunity to execute. For instance, in languages that utilize cooperative multitasking, developers must ensure their tasks yield control at appropriate times, usually during I/O operations or when explicitly instructed. However, in preemptive multitasking scenarios, the OS scheduler manages task switching, reducing the need for foresight in task management, but increasing the complexity of understanding and managing shared resources. Next, we will write a simple implementation that demonstrates cooperative multitasking using Python's generators. Here, we define a function called task, which simulates a task by printing a starting message, yielding control back to the scheduler, then resuming to print a resumed message followed by another yield, and finally printing a finished message when the task completes. We create 2 generator instances, Gen1 and Gen2, representing 2 tasks, A and B. The while loop that follows aims to execute each task in an interleaved fashion. Within this loop, we attempt to step through each generator using the next function. When a task is finished, it raises a stop iteration exception, which we catch to break out of the loop for that particular generator. This sequence showcases how generators can manage control flow manually, allowing tasks to yield execution voluntarily at designated points. Such control is fundamental in cooperative multitasking, as it promotes an organized method of task scheduling while underlining the importance of proper yielding to avoid blocking other tasks. This implementation sets the stage for discussing task scheduling nuances as we expand this model further. Now let's see how we can implement concurrency in Rust using the Tokyo framework. In this example, we define an asynchronous main function that serves as the entry point for our application. The Tokyo main attribute allows us to use asynchronous capabilities directly within the main function. We create two concurrent requests by calling requestHandler with different URLs. Each call returns a future which allows us to set up non-blocking operations. By awaiting these futures with await, we ensure that our main function will pause until each request is completed, at which point we print the responses. The requestHandler function demonstrates an asynchronous task where we simulate a delay using the sleep function from the Tokyo time module. This delay represents an I/O-bound operation, where the function will yield control during the sleep period, allowing other tasks to execute while waiting. After the delay, we format and return a message indicating the request has been handled. This structure showcases how tasks can run concurrently and effectively utilize the event-driven capabilities of the Rust programming model. In conclusion, concurrency is a vital concept for modern software development. Understanding its principles empowers developers to create applications that are not only efficient and responsive, but also scalable. As we've seen, languages have equipped us with a variety of tools and methodologies to manage concurrent operations effectively. As we continue to delve deeper into this subject, be prepared to explore more advanced concurrency models, such as reactive programming and event-driven architecture, enabling you to take full advantage of concurrency in your applications. Stay tuned for more exciting exploration into the realm of modern application design and performance optimization. We can broadly categorize abstractions over concurrent operations into two groups: high-level and low-level abstractions. In this segment, we'll focus on handling asynchronous operations, breaking down how these abstractions work and how they can be effectively utilized in modern programming. So far, we learned that concurrency is essential for building efficient and responsive applications, with the operating system coordinating tasks through asynchronous programming. We explored how concurrency enables multiple tasks to progress simultaneously, utilizing techniques like threading in Python and promises in JavaScript. We also discussed the importance of synchronization to prevent data inconsistency when managing shared resources in a concurrent environment. Lastly, we touched on the distinction between cooperative and preemptive multitasking, and how various programming languages offer abstractions to simplify concurrent programming. Now, we will delve into the world of asynchronous operations and how we can leverage both high-level and low-level abstractions to enhance our applications. Now let's take a look at how we can implement asynchronous operations using JavaScript's setTimeout function. In this snippet, we start by logging task 1, start to the console, signaling the initiation of the first task. The setTimeout function is then called, scheduling the execution of a callback function that logs task 2, delayed task completed after a 2-second delay. This is a crucial aspect of asynchronous programming, as it enables this logging to occur without blocking the execution of any subsequent code. Immediately after scheduling the setTimeout, we log task 3, continue with other work to the console. This demonstrates the non-blocking nature of the code. While we wait for the 2-second timer to elapse for the second task, the application doesn't freeze, instead it proceeds to execute the next line. Once the timer completes, the delayed task is logged. This approach enhances the responsiveness of applications, allowing for better user interactions by handling long-running processes concurrently with other work. Now let's take a look at how we can create and use promises in JavaScript to handle asynchronous operations effectively. The function fetchData is designed to simulate a network request by returning a promise. Inside this promise, we utilize the setTimeout function to create a deliberate delay of 3 seconds, mimicking the time it would take to fetch data from a server. At the end of the delay, we use the resolve function to return a successful response with the message data received. Additionally, a line is commented out that, if uncommented, would invoke the reject function to simulate an error scenario during the data fetch. This flexibility allows us to easily test how our application handles success and failure cases. Following the function definition, we call fetchData and chain it with the then method, which executes when the promise is successfully resolved. Here we log the received data to the console. In case of any errors, we catch them using the catch method and output the error message. This structure not only clarifies the flow of asynchronous operations, but also enhances readability and error management in our code. Next, we will write the following code to demonstrate the async await feature in JavaScript, which allows for a more streamlined approach to handling asynchronous operations. Here, we define an asynchronous function named fetchDataAsync. Inside this function, we utilize the await keyword to pause the function's execution until the promise returned by fetchData is either fulfilled or rejected. This makes the code easier to read by resembling synchronous behavior, as we can handle the result directly after the await call rather than chaining multiple then methods as we did with promises. If the fetchData promise resolves successfully, we log the received response to the console. Otherwise, we catch any errors that may occur during this process using a try-catch block. The catch clause allows us to gracefully handle any exceptions by logging the error to the console, ensuring that our application can respond appropriately to unforeseen issues. Finally, we execute fetchDataAsync, which triggers the asynchronous function, illustrating how we can manage asynchronous tasks effectively with this elegant syntax. Now let's see how we can implement asynchronous operations in Python using the Asyncio library. We start by defining an asynchronous function called fetchData, which simulates a data retrieval process. Inside this function, we print a message indicating that data fetching is in progress, and then we use await with Asyncio sleep 3, mimicking a non-blocking operation that pauses execution for 3 seconds before proceeding. This allows other tasks to run concurrently during this wait time. Next, we have the main function, where we initiate 2 tasks using Asyncio create task, both calling fetchData. This setup demonstrates concurrent execution of tasks. Instead of waiting for one task to finish before starting the other, both will run simultaneously. By awaiting each task in the main function, we ensure that our program waits for the completion of both before concluding. Finally, we call Asyncio run main to execute our asynchronous main function, effectively managing these I/O-bound operations and optimizing our application's responsiveness. Now let's implement a mechanism to manage the cancellation of asynchronous tasks in Python using the Asyncio library. In the following example, we define an asynchronous function named fetchData, simulating a long-running I/O operation with a sleep duration of 5 seconds. This function initializes by printing a message indicating that data fetching has started. However, to demonstrate how cancellation works, we wrap the operation within a try-except block. If the task is cancelled, a cancelled error is raised, allowing us to handle this situation gracefully by printing a message confirming the operation was cancelled. Next, in the main function, we create an event loop where we initialize a task that runs the fetchData function. After waiting for 2 seconds to simulate some processing time, we call taskCancel to cancel the ongoing data fetch operation. Importantly, we await the task to ensure that the cancellation process completes, thus preventing any unhandled exceptions. This code outlines how to efficiently manage task lifecycles by employing cancellation mechanisms, which are especially useful in scenarios where resources might be freed preemptively when no longer necessary. Now let's take a look at how error handling works in asynchronous programming using JavaScript. In this example, we define an async function called throwError, which is designed to purposely throw an error when called. This demonstrates how errors can arise in an asynchronous context. Next, we create another async function named main, where we use a try-catch block to handle the error gracefully. Inside the main function, we invoke the throwError function using the await keyword. This means that the execution of main will pause until throwError either resolves or throws an error. When the error is thrown, it triggers the catch block, allowing us to manage the error effectively without crashing the entire application. Here, we log the error message to the console, providing feedback on what went wrong. This approach not only maintains the stability of the application, but also ensures that users receive informative updates without exposing them to technical jargon or failures. Thus, wrapping asynchronous calls in try-catch blocks is essential in writing robust, user-friendly applications. As we wrap up our lesson on handling asynchronous operations, let's reflect on the key points. We explored the differences between high-level and low-level abstractions, learning how high-level constructs like promises and async await simplify the development of asynchronous code. We then moved on to low-level alternatives using tools like Python's Asyncio, which empowers developers to manage the details of concurrency and resource control effectively. We also discussed crucial practices such as canceling asynchronous tasks and handling errors gracefully, allowing our applications to remain responsive and robust in the face of unexpected scenarios. Ultimately, embracing asynchronous programming allows us to develop applications that handle heavy workloads efficiently while maintaining a smooth experience for users. So whether you're building a small script or a complex web application, understanding and leveraging these asynchronous concepts will undoubtedly enhance your development toolkit. Stay tuned for our next lesson, where we will explore more advanced concurrency patterns and their practical implementations. Now let's take a look at how we can implement an asynchronous function in Rust using the Tokyo runtime. The main function is mocked with the Tokyo main macro, which transforms it into an asynchronous entry point for our application. Inside this function, we create a future by calling fetchData, which encapsulates the working logic of our async task. Upon invoking this function, it doesn't block the thread but rather returns a future object that represents a value that will be available later. Next, we print a message indicating that we are fetching data, and then we use the await keyword on the future. This tells Rust to pause execution at this point and allow other tasks to run while waiting for the data. The fetchData function itself simulates a delay by calling sleep, which upon completion will yield the string hello from Rust. This showcases how Rust's model of async programming allows for efficient context switching, as the function is effectively transformed into a state machine that can seamlessly pause and resume execution. Thus, we achieve non-blocking behavior while keeping our application responsive. Now let's see how we can implement an asynchronous function in JavaScript using the async keyword. In this example, we define the function fetchData, which logs a message indicating that data fetching has started. Inside this function, we create a new promise that simulates a delay with setTimeout, resolving after 2 seconds. The use of await allows the function to pause execution until the promise resolves, giving the appearance of synchronous behavior while maintaining the application's responsiveness. As a result, this function will not block the execution of other parts of the program while waiting for the promise to resolve. After the delay, the string data received from JavaScript is returned, and we utilize the then method to handle the resolved value when the function is called. This structure illustrates the core principle of async programming in JavaScript, allowing tasks to proceed without interruption, thereby enhancing user experience. This approach is fundamentally similar to how Rust handles async operations, emphasizing the shared concepts of futures and promises in both languages. Now let's see how we can implement concurrency in Python using the Asyncio library. In this example, we define 2 asynchronous functions, fetchData from source1 and fetchData from source2. Each function simulates a delay in fetching data by using await Asyncio sleep, mimicking a time-consuming operation, where the first function waits for 3 seconds and the second for 1 second before returning their respective results. Next, we'll create a main function that sets up these 2 tasks. Instead of executing them sequentially, where one would have to finish before the other starts, we utilize Asyncio gather. This method allows us to run both tasks concurrently, taking full advantage of the event loop to manage these tasks efficiently. The results from both functions are awaited, and once completed, they are printed together. Finally, we call Asyncio run main to execute our main function and start the event loop. By harnessing the power of Asyncio, we effectively demonstrate how concurrency can significantly enhance the performance of applications by allowing them to perform multiple operations simultaneously without blocking the execution. Next, we will write the following example using JavaScript to illustrate how to manage task cancellation in asynchronous operations. In this code, we utilize the abort controller, which is a powerful tool for managing the cancellation of asynchronous tasks. We start by creating a new instance of abort controller, which provides us with a signal that we can monitor for cancellation requests. The fetchData function is defined to simulate a fetch operation, represented as a promise that resolves after 3 seconds unless it's aborted. Inside the promise, we check if the signal has been triggered to abort the operation, allowing us to reject the promise with an error if so. To demonstrate the cancellation, we call the fetchData function and attach an error handler to log any errors that arise due to abortion. Then we set up a timeout to call controlUbot after 1 second. This means that even though the fetch operation is still pending, it will be terminated early. As a result, we will see a message indicating that the fetch operation has been aborted, showcasing how effectively we can control the execution flow and responsiveness of applications, especially in the context of user interactions. Now let's take a look at a simple example of managing shared state in Rust using concurrency primitives. In this code, we first import the necessary modules for awk and mutex, which are essential for safe multithreading in Rust. Here, an awk atomic reference counted is used to enable multiple threads to own a reference to the same value, while mutex ensures that only one thread can modify the value at a time, preventing race conditions. Next, we initialize a counter variable wrapped in a mutex and an awk. We then create a vector to hold the thread handles. In a loop, we spawn 10 threads, each of which will attempt to increment the shared counter. By using awk clone, we share the same awk instance with each thread, allowing all threads to safely access the count variable. Within each thread, we lock the mutex to gain exclusive access to the counter, incrementing its value and then releasing the lock automatically when leaving the scope. After all threads have been spawned, we join them, ensuring they finish execution before moving on. Finally, we print the final value, demonstrating how effective synchronization enables safe concurrent access to shared state in Rust applications. Now let's take a look at how we can manage shared state in JavaScript using asynchronous functions and promises. In our example, we define a variable shared state initialized to 0, which will be incremented by multiple concurrent operations. To accomplish this, we create an asynchronous function called incrementState. Inside this function, we first capture the current value of shared state in a local variable temp before simulating a delay using an await statement. This design allows each function call to work with its own version of temp, thus preventing race conditions from affecting shared state. Next, we proceed to define another asynchronous function, runInParallel, which utilizes promiseAll to execute 3 instances of increment state at the same time. This method is crucial because it allows all increments to occur concurrently, demonstrating how JavaScript handles asynchronous operations effectively. Finally, we log the final value of shared state after all increments have completed. By approaching state management in this way, we can better understand how to handle shared variables across concurrent functions without running into unexpected results, showcasing the power of JavaScript's asynchronous model. Finally, let's touch on the idea of structured concurrency, a concept that aims to simplify the mental model around concurrent programming. It allows tasks to be neatly organized and cleaned up whenever they are no longer needed. In Rust, this can be managed through various libraries, while in JavaScript, adopting practices around async structures can help, such as using controllers to ensure tasks are properly terminated. In Rust, you might use crates like Async Nursery to manage multiple async tasks together in a clean way. In JavaScript, libraries like Async.js can help keep your asynchronous code organized, enabling you to handle multiple asynchronous tasks without the deep nesting often associated with callbacks. The aim here is to make your code more readable and maintainable by defining clear parent-child relationships over async tasks. To sum up, as we navigate through advanced topics in concurrency, we've explored how Rust and JavaScript treat async operations through futures and promises, the distinctions between concurrency and parallelism, and learned about managing state, handling cancellations, and implementing structured concurrency. As you embark on your journey into building efficient applications, grasping these concepts will not only enhance the performance of your software but also provide a smoother experience for users. Remember, with great power comes great responsibility. Embrace these tools mindfully, and you'll be well on your way to mastering concurrency. In this discussion, we will dive into the fascinating world of operating system event queues. Operating systems are highly adept at managing various events, and understanding how they handle these events is crucial for building efficient software. Today, we'll explore the implementation of event queues, how different operating systems manage them, and the impact on the performance of applications. Now let's implement a simple event queue using Python, which will help illustrate how events can be managed within an event-driven architecture. We begin by importing the deck class from the collections module, which provides a double-ended queue, allowing efficient appends and pops from both ends. Next, we define the event queue class, where the constructor initializes an empty deck to hold the events. This structure forms the backbone of our queue. The InQueue method allows us to add new events to the end of the queue, ensuring that they are processed in the order they arrive. To retrieve events, we use the dequeue method, which checks if the queue is empty before removing the event from the front of the queue. This ensures that we don't attempt to process events that aren't available. Additionally, the isEmpty method provides a straightforward way to check whether there are any pending events to process. To illustrate how this works in practice, we create an instance of the event queue and enqueue a couple of events. Finally, we have a simple loop that checks if the queue is empty, processes each event by dequeuing it, and prints a message indicating which event was processed. This structure highlights how an event queue can maintain responsiveness in an application by managing events effectively. Now let's take a look at a simple Windows message handler written in C++. This implementation centralizes event handling for GUI applications, showcasing how Windows manages its event-driven architecture through a message loop. The window procedure function acts as a callback that processes different messages sent to a window. It begins with a switch statement that distinguishes between various message types, such as wmpaint for repaint requests and wmdestroy, which signals the window's closure. In the case of wmdestroy, the function calls post-quit-message0, effectively terminating the application's event loop and allowing for a graceful shutdown. Following this, we have the main function, which initializes the message loop. Inside this loop, getMessage is called to retrieve messages from the queue and is responsible for blocking until a new message arrives. After fetching a message, translateMessage and dispatchMessage are executed, processing and forwarding the message for handling. This structure ensures that the application remains responsive, handling user inputs and system notifications efficiently while continually running. Through this code, we gain insight into the foundational principles of event management in a Windows environment, essential for building responsive GUI applications. Now let's take a look at how we can implement event monitoring in a Linux environment using the epoll interface. The code begins by including necessary header files for epoll and Unix system calls. We declare the main function, where we first create an epoll instance with epoll create1. This function initializes an epoll file descriptor, which will be used to monitor multiple file descriptors for events. Next, we set up the epoll event structure, which will define the type of events we are interested in. In this case, we specify epollin in event events to indicate that we want to monitor the file descriptor for incoming data. The actual file descriptor to be monitored is assigned to event data fd, which you'll replace with your specific file descriptor. Following this setup, we use epollctl to add the file descriptor to our epoll instance, registering it for monitoring. The main loop of the program employs epoll_wait, which will block until one or more events occur on the monitored file descriptors. Once events are detected, we can process each event in the loop, allowing efficient handling of multiple concurrent events without consuming excessive resources. Finally, we close the epoll file descriptor before the program concludes, ensuring proper cleanup. Now let's see how we can implement a basic macOS application that utilizes the event-driven architecture through the run loop. In this code, we start by importing the Cocoa framework, which provides the necessary features for building macOS applications. Next, we define the main function, which is the entry point of our application. Within this function, we create an auto-release pool, a common pattern in Objective-C that helps manage memory automatically, ensuring that any objects created within the pool are released when they are no longer needed. Inside the auto-release pool, we obtain a singleton instance of NS_application, which represents our application. This object is essential as it manages the app's lifecycle and serves as the central point for event handling. Finally, we invoke the run method on the app object, which starts the event loop. This loop continuously processes user inputs, system events, and timers, allowing the application to respond smoothly and efficiently to user interactions while maintaining high performance. Through this straightforward implementation, we leverage the power of macOS's event-driven model. Understanding event queues across these operating systems showcases the diversity in handling asynchronous operations. Every system implements its unique approach, combining performance optimization with user responsiveness. Regardless of the underlying implementation, the importance of properly managing event queues cannot be overstated, as it directly impacts the user experience. As you develop your software, remember that built-in event handling mechanisms significantly simplify the complexity of managing asynchronous tasks. You'll gain a clearer sense of control over your application's flow, facilitating effective user interactions without overwhelming system resources. In summary, we have explored the concept of operating system event queues, their general structure, and the way various operating systems like Windows, Linux, and macOS manage these queues. Each system applies its methodology, from the message loop in Windows GUI applications to the efficient epoll in Linux and the event-driven run loop of macOS. Equip yourself with this knowledge as you dive into building responsive applications that cater to modern user expectations. In conclusion, an understanding of event queues is increasingly essential in today's software landscape. Efficiently managing these queues can enhance responsiveness and performance in your applications. With the foundational knowledge of different approaches across operating systems, you're now prepared to implement and optimize event-driven architectures. Thank you for tuning in, and best of luck with your programming endeavors. Now let's take a look at a practical example of reading data from a file using system calls in C. In this code, we start by including necessary header files that provide access to standard I/O, Unix standard functions, and file control definitions. We declare an integer file descriptor, fd, to hold the reference to the opened file, along with a character array buffer to store the data we read. Next, we use the open system call to attempt to open example txt in read-only mode. If the file fails to open, the program calls para to output the corresponding error message and returns a non-zero value, signaling an error. If successful, the program proceeds to read data from the file into the buffer using the read system call, specifying the number of bytes to read. Again, we check for potential read errors, handling them gracefully by closing the file descriptor and returning an error status. If reading the file succeeds, we ensure the buffer is null terminated, making it a valid string. Finally, we print out the number of bytes read and the contents of the buffer to the standard output before closing the file descriptor. This code demonstrates how syscalls encapsulate file operations, allowing programs to handle files effectively while ensuring safe interaction with system resources. Now let's take a look at how we can write data to a file in C using the write system call. First, we begin by opening or creating a file called output.txt with the open function. The parameters specify that we want to write to the file and create it if it doesn't already exist, while also setting appropriate permissions. After checking that the file opens successfully, we prepare the message we want to write, "Hello World." Next, the code uses the write system call to send this string to the file. It's important to note that the write call returns the number of bytes written, which we check to ensure the operation was successful. Error handling is implemented. If something goes wrong during the writing process, the program returns with an error code. Finally, we close the file descriptor using the close function, which is essential to free up system resources. This example illustrates how system calls allow us to interact with file I/O in a straightforward manner while abstracting the complexities of the operating system's underlying processes. Now let's see how we can implement file writing using the C standard library functions. In this example, we utilize the fopen, fprint, and fclose functions to manage file operations more intuitively. The fopen function opens a file named output.txt in write mode, returning a file pointer. If the file cannot be opened, we handle the error gracefully by checking if the pointer is null and using para to display an appropriate error message. Once the file is successfully opened, we can write to it with the fprint function, which allows us to format the output similar to print but directed at the file instead of the console. Here we write the string "Hello World," followed by a newline character. Finally, we ensure that all buffered data is flushed to the file by calling fclose, which also closes the file, releasing any resources associated with it. By employing these higher-level abstractions, we enhance readability and maintainability of the code, making it easier to perform file I/O operations without delving into the lower-level system calls. Now let's see how we can implement process management through the fork syscall. In C, the code begins by including necessary headers for standard input-output operations and for using the fork function. In the main function, we invoke fork, which creates a new process by duplicating the calling process. The return value of fork is critical, as it differentiates between the parent and child processes. If fork returns a negative value, an error has occurred, and we handle this gracefully by printing an error message and exiting. When fork is successful, it returns a 0 to the child process and the child's process ID (PID) to the parent. This allows us to execute different code in each process. In the child process, we print a message indicating its PID, whereas the parent process prints its own PID along with the child's PID. This simple example effectively demonstrates how multitasking is achieved through process creation, enabling developers to handle concurrent operations without delving into the complexities of process management directly. By leveraging this abstraction, applications can perform tasks concurrently, enhancing overall efficiency and responsiveness. Now let's implement the following example, which demonstrates improved error handling in file operations. We start by opening a file called output.txt with the intent to write to it. The open function is used here with the flags OWRNLY and OCIAT, which indicate that we want to open the file for writing and create it if it doesn't exist. If the file opening fails, for instance, due to permission issues or problems with the file system, the function returns -1 and we use para to display a descriptive error message. Error handling is essential as it helps in diagnosing problems during runtime. Once the file is successfully opened, we define a message to write. We use the write function, which transfers the message from our program to the file. Again, we check if write returns to catch any issues during this operation. If an error occurs, we provide feedback through para and ensure the file is closed cleanly to release resources. Finally, if all operations succeed, we close the file and exit the program. This structured approach not only promotes good coding practices but also contributes to building robust applications by anticipating and managing potential errors effectively. Now let's see how we can implement the mmap system call to efficiently map a file into memory. First, we begin by opening the file example.txt in read-only mode using the open function, which provides a file descriptor that we'll work with throughout the program. It's crucial to check if the file opens successfully. If there's an error, we use para to print a descriptive message and exit gracefully. Next, we determine the size of the file using lseek, which allows us to navigate to the end of the file to retrieve its length. After that, we reset the file's offset to the beginning, preparing to map its content into memory. To achieve the mapping, we call the mmap function, passing it parameters that specify the starting address, length, permissions, in this case read-only, and a flag indicating private mapping. If mapping fails, we handle the error similarly and free the file descriptor. Once mapped, we can access the file's content as though it were in normal memory, enabling efficient read operations without unnecessary data copies. Finally, we print the mapped content and use munmap to detach the memory mapping before closing the file descriptor, ensuring that resources are properly freed. This use of mmap demonstrates an advanced technique for managing file data efficiently in memory. Now let's take a look at an example that demonstrates how to efficiently write multiple lines to a file using system calls. In this code, we begin by opening a file named output.txt in write-only mode, creating it if it doesn't exist. This is done using the open system call, which returns a file descriptor, an integer that we will use to refer to the file in subsequent operations. Next, we define an array of messages, each containing a string to be written to the file. The for loop iterates over this array, and for each string we call the write system call. This system call takes 3 arguments: the file descriptor, the message, and the length of the message. By batching our writes in this manner, we're effectively minimizing the number of syscalls made, which helps reduce overhead and improve performance. Finally, after writing all messages, we use the close system call to close the file descriptor, ensuring that all resources are properly released. This example illustrates the importance of using system calls wisely, as it highlights how to achieve efficiency and optimal performance while interacting with the file system. As we wrap up our exploration of system calls and abstractions, we've uncovered how they facilitate interaction between user applications and the operating system. Syscalls not only allow for secure and efficient resource management, but also enhance the ease with which developers can create complex applications through high-level abstractions. That's pretty powerful. Remember, the next time you're coding, whether it's file management, process creation, or networking, you're likely utilizing these system calls under the hood, silently working to make your application run smoothly. As developers, it's our responsibility to understand how these abstractions perform, optimize them, and utilize them effectively to create robust software that meets user expectations. In summary, we've covered the essential role of system calls, their structure, and how they abstract and manage resources within an operating system. Understanding these concepts is crucial for anyone pursuing a career in software development or engineering. Whether you're working with file I/O, memory management, or process control, the knowledge you've gained today will serve you well as you navigate the landscape of system programming. Thank you for joining me on this journey into the world of system calls and abstractions. When creating a cross-platform event queue, you have to deal with the fact that you must develop a unified API that functions the same on Windows, using IOCP, macOS using KQ, or Linux using epoll. In today's session, we're going to peel back the layers on how to build such a cross-platform event-driven architecture. We'll explore how event queues work, delve into specific implementations for each OS, and finally we will learn how to abstract these differences into a seamless API. So far we learned about system calls, their importance, and how they give us access to system resources while ensuring security. Now we will cover making event queues that are platform agnostic, allowing our applications to be more portable across different operating systems. To understand event queues, we first need to define what we mean by events. In the context of programming, events are basically actions or occurrences that happen in the system which your application can respond to. For example, user inputs, file changes, or network messages can all be considered events. The idea behind an event queue is to manage these events efficiently. An event queue collects events and dispatches them to the appropriate handlers in a way that minimizes blocking and optimizes response times. This is particularly important in applications that require high responsiveness, like user interfaces or servers handling multiple client connections. Let's begin with the foundations of our cross-platform event queues. Each operating system offers its own methods for handling events. In Windows, we utilize I/O completion pots (IOCP), while macOS adopts KQ and Linux prefers epoll. All these mechanisms are designed to efficiently manage I/O operations but differ in implementation details. While building a unified API, we can create a layer of abstraction to handle these differences. This allows developers to write code that makes use of events without worrying about the underlying platform specifics. Now let's take a look at the implementation of our Windows-based event queue using I/O completion pots. We begin by defining a thread function, threadproc, which will handle the completion notifications for I/O operations. Within this function, we specify a loop that continually calls getQueuedCompletionStatus, which waits for an I/O operation to complete on the completion pot. When an operation finishes, it retrieves the number of bytes transferred and prints this information to the console, showcasing how efficiently we can handle I/O events in a multi-threaded environment. Next, in the main function, we create a completion pot with createIOCompletionPot, which serves as the primary structure for managing our asynchronous I/O operations. We also initialize worker threads. 4 threads are created to handle events concurrently. This design allows for scalability, enabling the application to manage multiple connections efficiently. Finally, after ensuring that all threads complete their execution, we close the handle to the completion pot, ensuring that system resources are managed effectively. This structure of threading and event handling is pivotal for building a responsive and high-performance event-driven architecture. Now let's see how we can implement a basic event loop using KQ in macOS. In this code, we first create an event queue by calling KQ, which sets up our mechanism to monitor multiple file descriptors. After creating the event queue, we open a file descriptor for reading a sample file, example.txt. Next, we prepare a kevent structure using evset, configuring it to listen for read events on the opened file descriptor. Here, we specify the event filter for reading, and we add it to the active list for events to monitor. The main loop is where the magic happens. We call kevent to block and wait until any registered events occur. If an event is triggered, which indicates that the file descriptor is ready for reading, we then print a message signaling that the file is ready to be processed. This approach showcases the non-blocking nature of KQ, allowing our application to respond efficiently to I/O operations without unnecessary delays. By understanding this structure, we can build responsive applications that leverage efficient event handling principles. Now let's see how we can implement an event loop using the epoll mechanism in Linux. We start by creating an epoll instance with the function epoll create1, which generates a new epoll file descriptor. This file descriptor is then used to manage our interest list, a collection of file descriptors we want to monitor for events. Next, we open a file, in this case example.txt, for reading and set up an epoll event structure. We specify that we are interested in monitoring this file descriptor for read events by setting the appropriate flags. Following that, we add the file descriptor to the epoll interest list using epollctl, which registers our interest in the specified events for this descriptor. The main loop begins with epoll wait, which blocks the execution until one or more events occur on the monitored file descriptors. When an event is detected, we iterate through the reported events and check if the event corresponds to a readiness for reading. If so, we output a message indicating that the file descriptor is ready for reading, allowing us to handle the data accordingly. This pattern enables efficient management of multiple I/O operations with minimal overhead. Now let's see how we can implement a cross-platform interface for handling events in our application. The code uses preprocessor directives to distinguish between different operating systems, allowing us to define an event queue in a way that fits seamlessly with Windows, macOS, and Linux. For Windows, we create an event queue using the handle, type, and define functions that leverage the createCompletionPot and createCompletionPot methods, which are optimized for asynchronous I/O operations. In macOS, we utilize kqueue, defining our event queue as an integer while using evset to manage events for file descriptors. For Linux, we again define event queue as an integer, employing the epoll create1 and epoll ctl functions to handle multiple file descriptors efficiently. The function processEvents is structured to provide platform-independent event processing logic. This encapsulated approach allows you to handle events generically, while the underlying implementation details differ based on the OS. By utilizing this cross-platform design, you enable a unified way to manage event-driven programming, simplifying the complexity involved in developing applications for multiple platforms. Now let's implement the processEvents function, which acts as the event processing loop for our cross-platform event queue. This function takes an event queue and a callback function as parameters, enabling it to manage event handling in a way that is agnostic to the underlying operating system. The infinite loop within the function ensures continuous monitoring of the event queue, providing a robust mechanism for event processing. Inside the loop, we use preprocessor directives to differentiate the implementation based on the operating system. For Windows, we would include specific code that takes advantage of the I/O completion pots, while macOS would utilize kqueue and Linux would leverage epoll. This conditional compilation allows us to write tailored event processing logic that maintains high efficiency on each platform. After processing the events suitable for the current operating system, the callback function is invoked with the file descriptor as an argument. This enables the respective event handlers to perform their designated actions based on the events processed, providing flexibility and responsiveness as required in a cross-platform architecture. In summary, we have explored the concept of event queues in cross-platform applications. By understanding the different implementations available in Windows, macOS, and Linux, we developed our custom API that abstracts these underlying details. This allows for seamless coding across different platforms without needing to worry about the specifics of each operating system. We also saw how to implement a processing loop that can call appropriate callbacks when events occur, which is essential for responsive and efficient applications. By mastering this, you'll not only write code that's clean and maintainable but also significantly increase the performance of your applications across platforms. In the future, we will dive deeper into more advanced concepts like handling multiple types of events simultaneously and improving on the performance of our event-driven architecture. But for now, you have the foundational knowledge to create your own cross-platform event queues. Happy coding! In this video, we're diving into the fascinating world of epoll, a powerful mechanism for handling event notifications in Linux. We will explore its features, how it works, and guide you through creating a simple version of an event queue inspired by the Mio library, which underpins the Rust asynchronous ecosystem. So far, we've covered the creation of a cross-platform event queue, focusing on a unified API that works across Windows, macOS, and Linux. We discussed the importance of efficiently managing events through mechanisms like IOCP, kqueue, and epoll. This foundational knowledge sets the stage for our current exploration of epoll, where we will see how it can help enhance application performance in managing numerous simultaneous events. To kick things off, let's establish what epoll is. At its core, epoll is a Linux-specific event notification interface that allows applications to efficiently monitor multiple file descriptors to see if they are ready for I/O operations. While traditional techniques like select and poll are usable, they come with their own limitations, especially with a growing number of file descriptors. This is where epoll shines, providing a scalable solution by allowing the kernel to manage the monitoring of events for us. An important concept to grasp is that epoll operates in a non-blocking manner. This means that you can continue running your application while waiting for events to occur, as opposed to halting execution and waiting for an I/O operation to complete. This is crucial in building responsive applications, especially for servers handling multiple clients. Now let's see how we can implement the initialization of our Rust project. We start by using the command cargo init epoll, which sets up a new project directory and prepares it for our epoll implementation. This setup is essential as it provides the necessary structure for organizing our code, allowing us to focus on building specific modules relevant to our event queue. Next, we will write the contents of our FFI RS module, where we declare constants related to epoll operations and define the necessary external functions to interface with the C library. This includes constants like epoll for adding file descriptors to the epoll instance, epoll for monitoring file descriptors for readability, and epoll for edge-triggered events. We then declare extern functions such as epoll create, which creates a new epoll instance and returns a file descriptor. This module lays the foundation for interacting with the underlying system calls required for our event handling logic. Moving on to poll RS, we will establish a poll struct that encapsulates our epoll file descriptor. The new method creates this instance, and the poll method allows us to wait for events interacting with the epoll wait function. Both methods are vital for managing the lifecycle of our event queue. Finally, we implement event registration logic in the registry struct, which allows us to specify interest in events from TCP stream sources, effectively linking our Rust application with the underlying epoll functionality. Next, we will implement the cost structure for our event queue using epoll. We start by defining a poll struct, which will hold the raw file descriptor for our epoll instance. The new method is crucial. Here, we create the epoll instance by calling the epoll create function from our foreign function interface, ensuring we handle any errors that may occur during its creation. Now let's take a look at the poll method. This method utilizes epoll wait, which blocks until events are ready to be processed, populating the provided vector with the events that occurred. It also gracefully handles errors, adjusting the length of the events vector based on the actual number of events reported. Next, we'll need to implement a mechanism for registering interest in specific events, which we will manage through a separate registry struct. The register method in this struct will allow us to add TCP stream instances to our epoll instance, informed by the types of events we want to monitor. This modular setup keeps our event management organized and efficient, allowing us to track and respond to multiple streams effectively. Now let's see how we can implement the registry structure along with its registration method. This segment allows us to register a TCP stream with epoll, which is essential for monitoring events on specified streams. Within the register method, we first create an event instance, which encapsulates the interests for the event and a unique token identifier for the stream. This token acts as a reference, enabling us to efficiently manage which TCP stream triggered a particular event in the future. Next, we use the epoll-ctl syscall to inform the epoll instance about our interest in specific events for the TCP stream. By passing the parameters such as the raw file descriptor of the epoll, the operation type set to epoll-ctl, and the TCP file descriptor, we register the event. If the registration fails, we return an error using EO, error last OS error, ensuring that issues are properly handled. If successful, the method completes by returning an OK, signaling that the stream is now being monitored for the specified events. This setup is crucial in building responsive applications that handle asynchronous I/O efficiently. Now let's dive into the main execution in main RS, where we will set up the foundation for handling events using our poll instance. First, we need to import our necessary modules, specifically FFI for interfacing with the epoll API and poll for our polling logic. In the main function, we initialize a new poll object, which represents our event queue and allows us to manage file descriptors efficiently. Next, we will see how we can establish connections with different clients by creating instances of TCP stream. It's crucial to configure these streams as non-blocking to ensure that our application remains responsive while waiting for events. Once we have our streams, we will register them with our poll instance, signaling our intent to monitor them for incoming data or events. This setup will ideally allow our application to handle multiple clients effectively. After this configuration, we typically send requests to a server and await responses, setting the stage for active event management. In the following sections, we will focus on implementing the logic to handle these events and process incoming data efficiently. Next, we will write a helper function to format our HTTP GET requests, which is essential for communicating with our server, delay server. This function called getRec takes a string argument representing the path of the resource we want to access. It constructs a properly formatted HTTP GET request, including the necessary headers such as the host and connection fields. Using Rust's format macro, we concatenate the GET request line, the headers, and the required double newline that signifies the end of the HTTP headers. The result is then converted into a vector of bytes to be sent over the network. This function is crucial as it ensures that our requests comply with the HTTP protocol standards, making it easier for the server to interpret them. By encapsulating this logic in a separate function, we create a clean and reusable component that can be easily called whenever we need to issue a new request to delay server. With this setup, we are now equipped to send requests and handle the server's responses effectively as part of our event-driven architecture. Now let's implement the function to handle incoming events from our TCP stream. This function, handle events, takes in a slice of events and a mutable vector of TCP streams. It iterates over the events received from the epoll mechanism, where each event contains a token that we use to index into the streams. For each event, we create a buffer to read data from the corresponding TCP stream. It's essential to ensure that our index handling fits well, using the events token properly to avoid any potential out-of-bounds errors. Once we read from the stream, we convert the bytes into a human-readable string using string from UTF-8 lossy, which allows us to safely handle any invalid UTF-8 sequences that may be present. This output is then printed to the console, giving real-time feedback on the responses received from the delay server. It's crucial to consider that reading from a non-blocking stream might yield no data. Hence, this function could be expanded to handle such cases more gracefully. With this function in place, we can now effectively react to incoming data in our event-driven architecture. Now let's implement a continuous polling mechanism to monitor events efficiently. In this section, we create a mutable vector of events which acts as a storage for any incoming notifications from the epoll interface. The loop we set up is crucial because it keeps the application running, allowing it to block until events are ready to be processed. This means that instead of repeatedly checking for events in a busy waiting fashion, the loop will pause until the kernel signals that there are events to handle. As events are detected, we invoke the handle events function, passing in the vector of events along with our streams. This function processes each event, allowing the application to respond appropriately, such as reading data from a TCP stream and displaying the output. This structured approach leverages the non-blocking nature of epoll, ensuring that our application remains responsive and efficient while managing multiple simultaneous connections, especially important in a server environment. By using this polling strategy, we can simplify the flow of handling asynchronous events and maintain optimal performance. In summary, today we've explored the elegant but intricate world of epoll. We created a simple event queue using Rust, inspired by the Mio library's design. We outlined the purpose of epoll, established its API through system calls, created event structures, and implemented both registration and event handling. As you advance in your understanding of epoll and asynchronous programming, you'll find endless possibilities for creating powerful and efficient applications. Dive deep into the Mio repository or even consider integrating with more complex systems. Happy coding! If you have any questions or would like to see more examples, feel free to leave comments below and don't forget to subscribe for more tutorials like this. In this lesson, we'll dive into creating the poll module in Rust, a vital part of managing file descriptors for I/O operations. This module leverages the epoll interface to efficiently monitor multiple streams of input and output. So far, we learned about epoll and its advantages over traditional methods for managing file descriptors. Now, we will cover how to build the poll module, implementing necessary functionality while using placeholders that allow our program to compile without crashing. To start off, when we implement functions in our Rust code and aren't ready to fill in the details, we often use the to-do macro. Placing to-do in a function allows the code to compile, but if this function ever gets called during execution, it will panic and terminate the program. Think of it like putting a work-in-progress sign on your function. It's a helpful way to make sure our structure is sound without getting bogged down in the specifics before we're ready. Now let's take a look at the structure we've defined for our poll module. The poll struct encapsulates our functionality, holding a single field, raw fd, which is an integer representing the file descriptor for our epoll instance. This structure is essential as it serves as the foundation for our module, allowing us to efficiently manage file descriptors needed for monitoring I/O operations. Next, we will implement the new method for the poll struct. This method will create a new epoll instance by calling the epoll create system call, indicating our intent to monitor I/O events. Importantly, we wrap this call in an unsafe block due to its interaction with the C library. If the file descriptor creation succeeds, we return a new instance of poll initialized with raw fd. Conversely, if the call fails, we capture the lost error and return it, reinforcing Rust's principle of safe error handling. After establishing our poll struct and its initialization method, the next step will be to build polling functionality that uses the epoll wait function. This method will retrieve events for our registered file descriptors in a thread-safe way, allowing our application to listen efficiently for activity on multiple streams. Now let's see how we can implement the new method for our poll struct. This method is crucial as it initializes a new epoll instance by calling epoll create, a system call that returns a file descriptor. We encapsulate this call within an unsafe block because it directly interacts with the underlying C library, which requires careful handling. The method begins by attempting to create the epoll file descriptor, and if this operation returns a negative value, it indicates an error has occurred. In such cases, we leverage Rust's error handling by capturing the lost system error and returning it wrapped in a result. This is a common practice in Rust, prioritizing safety and clarity in error management. If the call is successful, we return an instance of our poll struct, complete with the newly allocated file descriptor, allowing us to manage multiple file descriptors efficiently as we progress with our poll module. This structured approach not only lays the foundation for robust error handling, but also demonstrates the core interactions with system resources in Rust. Now let's implement the polling functionality within our poll struct. We define the poll method, which accepts a mutable reference to a vector of events and an optional timeout value. The method starts by determining the timeout duration, defaulting to -1 for infinite blocking if none is provided. Then we utilize epoll wait, passing the raw file descriptor of our poll instance, the mutable pointed to our events vector and the timeout. This call is wrapped in an unsafe block since it interacts with the underlying C library. Next, we check the return value of epoll wait. If it's negative, an error occurred and we handle it by returning the lost OS error. Assuming success, we adjust the length of the events vector to correspond to the number of triggered events reported by epoll wait. This is crucial for our application's efficiency, as it allows us to process only relevant events. Ultimately, we finalize this method by returning an OK to indicate successful execution, efficiently managing our application's responsiveness across multiple file descriptors. Now let's implement the registry struct, which is responsible for managing file descriptor registrations with our poll instance. The registry struct contains a field called poll, which holds our poll instance, allowing us to encapsulate its functionality. Next, we will write the register method within the registry, which takes a TCP stream, a token, and a set of event interests as parameters. This method is crucial as it prepares an event struct that defines the event types we're interested in, such as whether we want to monitor for reading or writing. Here, we assign the event's properties accordingly, including converting the interests to the appropriate data type. Following that, we utilize the epollctl function to add the file descriptor associated with the TCP stream to our epoll instance. If this call is successful, the file descriptor will be monitored as specified. However, if it encounters an error, we handle it gracefully by returning the lost error captured from the system. This approach ensures our registration process is robust and keeps our program responsive as it interacts with I/O operations. Now let's implement the handle events method, which will process events generated during polling. In this method, we begin by iterating through the array of events that have been triggered. Each event contains an epoll data field, which acts as an index pointing to the relevant TCP stream in our stream's vector. This allows us to efficiently determine which stream corresponds to the event under consideration. For each event, we prepare a buffer to hold incoming data, reading from the corresponding TCP stream into this buffer. After reading, we capture the number of bytes that have been successfully read. We then print the received data to the console, converting the byte buffer into a human-readable string format using string from UTF-8 lossy. This step not only confirms that our application is functioning correctly by displaying incoming data, but also provides a useful debugging tool. By utilizing this method, we ensure that the application can respond to events appropriately, thereby enhancing its interactivity and robustness during I/O operations. Now let's implement the drop trait for our poll struct to ensure proper resource management. By doing this, we define how a poll instance should behave when it goes out of scope. specifically focusing on closing the file descriptor we obtained during its creation. The drop method is automatically invoked by Rust when the instance is no longer in use, and this method will call an unsafe function to close the raw file descriptor using FFI, close. The unsafe block allows us to bypass Rust's strict safety checks, as we are directly interacting with low-level system resources. Properly closing the file descriptor is crucial in avoiding potential resource leaks, which can lead to our application exhausting available file descriptors over time. With this implementation, whenever an instance of poll is dropped, it ensures that the allocated resources are released appropriately, safeguarding the stability and efficiency of our application. This method is a key aspect of Rust's ownership model and emphasizes the importance of managing system resources effectively to prevent memory leaks and other runtime issues. Now that we've constructed our poll module from the ground up, we can see how each piece fits together to create a robust system for managing events in an asynchronous manner. Each aspect we built, from the core struct to the methods handling registration, polling, and event processing, demonstrates how we can efficiently manage multiple file descriptors using Rust and the epoll interface. As we continue our learning journey, remember this is just a stepping stone. This foundation allows us to explore more intricate networking capabilities and improve our application's efficiency and responsiveness. I encourage you to experiment with modifications, try adding different event types, or even tackle error cases that we haven't covered in depth. Next time, we'll dive deeper into integrating this poll module with TCP clients and bringing everything together in a real-world application. So until then, keep coding and enjoy the journey. Now let's dive into handling events in our main program. This is a vital part of successfully utilizing the poll module we have implemented. Today, we will explore how to connect our poll module with TCP clients and how to handle events when they occur. So far, we learned about creating a poll module in Rust, which utilizes the epoll interface for managing file descriptors efficiently. We explored struct definitions, the implementation of methods like new, poll, and register, and how to handle events through the handle events method. Additionally, we focused on proper resource management by implementing the drop trait to ensure file descriptors are closed when no longer needed. Next, we will connect this poll module with TCP clients to apply our knowledge in a real-world scenario. Now let's take a look at how to establish a TCP listener in our program. We begin by binding the listener to a specific IP address and port, in this case, 127.0.0.1.8080. This binding allows our server to wait for incoming connections from clients on that specified address. The expect method is used for error handling, ensuring that if the binding fails, we receive a clear message indicating the failure reason. Next, we set our listener to non-blocking mode. This is crucial for efficiency, as it enables our program to continue performing other operations while waiting for incoming connections, rather than getting stuck. By using non-blocking mode, we can handle multiple clients concurrently without interrupting service for others. This approach is essential for building responsive applications, especially when we anticipate high traffic. Establishing this listener sets the stage for the next steps of our program, where we will implement the logic to accept and process incoming client connections effectively. Now let's see how we can implement our main loop for accepting incoming client connections. We start by creating an instance of our registry, which contains the polling mechanism and an empty vector to keep track of incoming streams. This allows us to handle multiple client connections efficiently. In the loop, we utilize listener_accept to check for new connections from clients. When a new client connects successfully, we set their stream to non-blocking mode, enabling our program to continue processing other connections without delay. After making the stream non-blocking, we proceed to register it with our poll instance using the register method, passing the stream and its index within the incoming stream's vector. This index will be helpful later for polling events related to the specific stream. If there are no new connections, we handle the woodblock error gracefully, allowing our loop to continue running smoothly. Overall, this approach efficiently monitors for new client connections while preparing to manage them as they occur in real time. Now let's implement the polling logic in our loop to efficiently handle events on the registered streams. We begin by allocating a vector called events, size to hold up to 128 event instances. This vector is essential for capturing the events generated during polling. Next, we set up a loop that continuously calls the poll method from our registry, passing the events vector along with a specified timeout of 100 milliseconds. This timeout allows the loop to check for events regularly without blocking indefinitely if there are none. If poll detects any events, it returns the number of occurrences detected. We then iterate through the detected events using a simple for loop. For each event, we retrieve it based on its index and call the handleEvents function to process the event appropriately for the corresponding TCP stream. This method encapsulates the logic for responding to various events, ensuring that our application can handle multiple connections seamlessly and respond to each one as needed. Implementing this polling mechanism is crucial for achieving an efficient non-blocking server model. Now let's implement the handleEvents function, which is vital for interpreting incoming events from clients. This function begins by checking if the event indicates that the relevant stream is ready for reading, which is essential for non-blocking I/O operations. If this condition is met, we extract the index associated with the event and prepare a buffer to read incoming data from the corresponding TCP stream. Upon successfully reading data, we print it to the console to verify that our server has received the expected information. Following this, the code constructs a simple HTTP response to send back to the client, assuming a basic format of an HTTP response. The response, indicating a successful connection with a status code of 200 OK, is then written back to the stream, signaling to the client that their request has been processed. This mechanism not only facilitates communication, but also illustrates how our server can handle multiple concurrent requests efficiently. By integrating this event handling, our application gains the ability to react to client interactions in real time, enhancing its responsiveness and performance. As we work through the event handling mechanism, it's also essential to ensure everything is efficient. The model we settled on using non-blocking connections and an event loop allows multiple clients to be served simultaneously. However, if you want to scale up or handle more complex operations, you might move further into async programming using Rust's async await features or look into using libraries designed for asynchronous I. For now, let's summarize what was accomplished. In our journey, we established a TCP listener that can accept incoming connections. We registered those connections using our earlier defined poll module, set our application to respond to events in non-blocking mode, and finally defined a handleEvents function to process and respond to client requests efficiently. Overall, a well-structured event handling routine like this provides a foundation for building scalable networked applications. As you code along and play with these functions, consider how you might extend the application. What if you wanted to implement different kinds of responses depending on specific requests, or perhaps log connection attempts? Exploring these avenues will deepen your understanding of network programming in Rust. To wrap up, always remember that handling events is the heart of creating interactive applications. Whether you're processing incoming requests, responding to user actions, or simply managing system events, the principles you've learned today are universally applicable. If you run into obstacles, remember to break down each part into manageable pieces as we've done. Now it's your turn to get hands-on with this knowledge. Try creating your own server using the steps we discussed, and don't hesitate to tweak the response handling or experiment with new features. The world of Rust and networking is vast and full of possibilities for you to explore. Keep pushing your limits and happy coding. In this tutorial, we're diving into the fascinating world of fibers, a powerful way to manage concurrency in our programs. This approach, often likened to coroutine or green thread implementations, offers an interesting twist on traditional threading, allowing for lightweight, efficient management of concurrent operations. So far, we covered the essential aspects of handling events in our program, especially around managing incoming TCP requests efficiently. We established a TCP listener that accepts connections in non-blocking mode, allowing for concurrent client handling. Additionally, we registered these connections within a polling mechanism and defined the handleEvents function to process client data and send responses. This foundation sets the stage for building scalable network applications and encourages exploration of advanced networking concepts in Rust. Now let's transition into fibers, understanding their workings and how we can create our own implementation. Now let's take a look at the foundational components we've implemented to build our fiber runtime. We begin with a runtime struct that maintains a collection of threads or fibers and keeps track of which thread is currently executing. Each thread is represented by a thread struct containing its own stack, execution context, and state, which can be either available, running, or ready. This classification is crucial as it allows us to manage the state of each fiber independently. Next, we define the thread context struct, which stores the CPU registers needed for context switching. By saving these registers, we can pause and resume the execution of fibers seamlessly. This leads us to the core functionality of our fiber scheduler. In the tyield function, we cyclically check the states of available threads and switch the execution context to one that is ready to run. Using inline assembly for context switching ensures that we do this efficiently, minimizing overhead. Following this, we implement a method to spawn new fibers. This process involves initializing the stack properly and aligning it, ensuring that when we call a function in our newly spawned thread, it operates smoothly. Each new fiber is prepared with its starting state, allowing it to run concurrently with others. This elegant design maximizes resource efficiency in handling concurrent operations and reinforces the foundation of our fiber implementation. Now let's take a look at how we implement the tyield function, which serves as our scheduler for managing fiber execution. This function primarily orchestrates context switching by iterating through the available threads to find one that is ready to run. We begin by checking the state of each thread, and if it is not ready, continue searching in a cyclic manner. If no threads are found to be in a ready state, the function returns false, indicating that no threads are available for execution. For threads currently running or available, the function updates their states appropriately. Notably, it marks the current thread as ready if it is not available and sets the state of the selected thread to running. The core of this implementation leverages inline assembly for context switching, ensuring low memory overhead and maintaining performance efficiency. By using asm to call the switch function, we yield control from the current thread to the chosen thread seamlessly. This mechanism is essential for creating responsive applications while efficiently managing the execution of lightweight fibers. Through this function, our runtime can effectively handle the execution flow of multiple fibers without incurring the overhead typical of traditional thread management. Now let's implement the function to spawn new fibers within our runtime. This function begins by searching for an available thread in our thread pool, which is crucial for ensuring that we do not attempt to spawn more fibers than our resources can handle. Upon finding an available thread, we retrieve its stack size and utilize unsafe Rust operations to set up the stack correctly for the new fiber. We adjust the stack pointer to ensure it is aligned properly to 16 bytes, which is essential for calling conventions and avoiding potential crashes. The function expects a callback, which represents the task to be performed by the fiber. We write the guard, skip, and function pointers to the stack. This setup is pivotal because it defines what the fiber will execute when it is scheduled to run. Finally, we mark the thread's state as ready, indicating it is now prepared to be scheduled by our fiber manager. This careful manipulation guarantees that we can seamlessly switch execution states when context switching occurs, thus enabling our fibers to run concurrently in a lightweight manner. Now let's implement the main function that demonstrates the concurrent execution of multiple fibers. In this section, we initialize the runtime environment to manage our fibers and set up two separate tasks. Each task represents a fiber function that prints messages and counts in a loop. First, we create a runtime instance which prepares our environment to spawn and manage fibers. The init method may set up necessary resources, but here we focus on spawning fibers. We then define the first fiber with a closure that prints a starting message and counts from 0 to 9, yielding control back to the scheduler after each iteration. This yielding allows other fibers to execute, ensuring that our model functions concurrently. The second fiber does something similar but counts to 14. After defining both fibers, we call runtime.run, which starts executing our fibers, allowing the runtime to switch between tasks as they yield control. This interleaved execution demonstrates the effectiveness of our fiber implementation, showcasing how they can operate concurrently without the overhead associated with standard threading. Upon running this code, observe the interleaved output of both fibers, confirming that our concurrency model is working as intended. The advantages of using fibers over traditional threads are notable, especially in terms of reduced context switching overhead and increased efficiency for handling lightweight tasks. The flexibility they provide brings a new layer of programming paradigms into Rust, allowing for innovative designs in concurrent applications. As you've seen throughout this tutorial, implementing fibers requires a bit of low-level manipulation, especially around stack management and context switching. However, it's these fundamental concepts that make understanding concurrency clear and powerful. In conclusion, mastering fibers opens up a world of possibilities for concurrent programming in Rust. With this foundational knowledge, you'll be well positioned to explore more advanced topics like asynchronous programming models and even libraries that enhance concurrency further. Remember, experimenting with the code provided and tweaking it can help deepen your understanding and may lead to discovering creative solutions to concurrency challenges in your applications. Happy coding! Now let's take a look at the tyield function, which is essential for our scheduler's task management. This function begins by setting a position pointer to the current fiber's index and enters a loop to search for a fiber in the ready state. If it encounters a fiber that is not ready, it increments the position pointer, wrapping around to the start of the list if it reaches the end. If it circles back to the original position without finding any ready fibers, it will return false, indicating that no threads are available to execute. Next, if the current fiber is not marked as available, it is transitioned to the ready state, allowing it to be considered for future scheduling. The scheduler then marks the fiber found at the new position as running, effectively switching control to it. The context switching is performed using inline assembly, which enables direct manipulation of the CPU state for the fibers, ensuring performance efficiency. This allows the system to save the state of the current fiber and switch to the next without unnecessary overhead, facilitating a smooth and effective concurrency model. In summary, this function encapsulates the core logic of our fiber scheduler, managing state transitions and enabling efficient context switching to enhance concurrency in our application. Now let's take a look at the structure of our thread, which is essential for managing fibers within our scheduler. This structure encapsulates the necessary components for each fiber, including a stack to hold its execution context, a thread context structure for storing the register states during context switches, and a state indicator that shows whether the fiber is available, running, or ready. Each of these attributes is crucial for the effective operation of our scheduler, as it provides the information needed to manage the fiber's lifecycle. Next, we will implement the runtime that maintains a collection of these threads. The runtime structure holds a vector of thread instances with an index that points to the currently executing fiber. By centralizing the management of these fibers within the runtime, we ensure efficient handling of scheduling, state transitions, and context switching. This organization allows our scheduler to quickly iterate over the threads and easily track which fibers are active, facilitating a seamless execution flow in our concurrent model. Now let's take a look at the runtime struct, which serves as the backbone of our fiber scheduling system. This structure contains a vector of thread instances, each representing a fiber along with its stack, context, and state. The current field indicates which fiber is currently executing, centralizing our scheduling logic. Next, we will implement the new function. This function initializes the runtime by creating the specified number of threads based on the maxthreads constant, preparing them with default states. Each thread is allotted a stack of predetermined size, and it starts in the available state, making it ready for future execution. We will also develop the spawn method, which is essential for adding new fibers to our runtime. This method searches for an available thread within the thread's vector and prepares its execution context. To ensure the correct alignment of the stack, we employ careful pointer arithmetic and mark the function to be executed. Finally, we transition the thread's state from available to ready, indicating it is prepared to be scheduled. These constructions lay the framework for an efficient fiber scheduling model where the runtime manages the life cycle and context of each fiber effectively. Now let's see how we can implement the main function, which initializes our runtime and spawns fibers for concurrent execution. This is where we create an instance of our runtime struct, allowing us to manage threads effectively. We first spawn the first fiber, which is defined by a closure that begins with a print statement. Inside this closure, a loop runs 10 iterations, printing the iteration count. At each iteration, the fiber yields control back to the scheduler using runtime yield, ensuring that other fibers get a chance to run and preventing any single fiber from monopolizing CPU time. Next, we introduce a second fiber in a similar manner, which runs concurrently with the first. This fiber also prints its iteration count, but it executes 15 iterations before signaling that it has finished. The repeated use of runtime yield in both fibers facilitates the switching of control between them. Finally, we call runtime.run, which triggers the scheduler to manage the execution of our fibers, allowing them to run until completion. This structure emphasizes how efficiently we can manage lightweight concurrency within a single thread, demonstrating the powerful capabilities of our fiber library. The run function would typically iterate through the fibers and invoke the scheduler we implemented earlier, allowing our fibers to run to completion while managing their states dynamically. This design encourages parallelism and more efficient CPU usage, which is essential in modern applications that require high levels of responsiveness. In summary, implementing the scheduler is a keystone for managing fibers effectively. It allows us to determine the execution order among multiple tasks, balancing their demands and ensuring that our application's responsiveness is maintained. As we have explored, the scheduler introduces mechanisms like context switching and thread management that are imperative for creating robust concurrent applications with fibers. By understanding this concept, you will have a solid foundation upon which you can build more complex concurrency behaviors and optimizations using Rust's fiber model. Embracing the spirit of concurrency opens up numerous possibilities, allowing for innovative solutions to common problems encountered in programming. As you delve deeper into this space, remember that effective scheduling and resource management can greatly enhance the structure and behavior of your applications. Keep experimenting, tweaking the code, and have fun while discovering new paradigms in concurrent programming. Happy coding! Now that we have covered one of the largest and most difficult examples, let's shift gears and explore another popular way of handling concurrency in Rust: how futures and async await work. This powerful paradigm allows developers to write asynchronous code in a more readable and maintainable way, making it an essential tool in modern Rust programming. So far, we learned about the implementation of a scheduler integral to our fiber runtime, which manages task execution by determining which fiber runs next. We established a foundational understanding of fibers, their states, and how to efficiently switch contexts without incurring significant overhead. We also explored the structure of both threads and the runtime, enabling seamless scheduling and concurrent execution of multiple fibers. This knowledge sets the stage for further exploration of advanced concurrency concepts in Rust, specifically through the mechanism of futures and async await. Now let's take a look at how we can implement the basics of using futures and async functions in Rust. We begin by defining an asynchronous function, fetchData, which simulates a network request. This function is marked with the async keyword, signifying that it will perform operations that can yield control back to the runtime, enabling other tasks to run while it waits. Within fetchData, we introduce a delay using Tokyo time sleep, which pauses execution for 2 seconds to mimic the time taken for a network request. The use of await indicates to the Rust compiler that we want to wait for this delay to complete before proceeding to the next line of code. Next, we define the getFutureExample function, which calls fetchData and returns a type that implements the future trait. This design allows us to obtain the future returned by fetchData, enabling the caller to continue executing other code concurrently, only waiting for the result when needed. This non-blocking nature of futures is a cornerstone of asynchronous programming in Rust, making it a powerful tool for handling I/O-bound tasks efficiently. Now let's see how we can implement a simple asynchronous main function using Tokyo, one of the most popular async runtimes in Rust. We begin by using the Tokyo main attribute macro, which sets up the asynchronous environment necessary for running our program. Within the main function, which is marked as asynchronous with the async keyword, we can call our previously defined asynchronous function getFutureExample and await its result. This is crucial as the await keyword indicates that we are pausing execution until the fetchData future completes, ensuring we do not block the thread during this wait. Once the future resolves, we receive the result and proceed to print it to the console. This straightforward implementation demonstrates the efficiency and readability of managing asynchronous operations in Rust. By leveraging Tokyo, we can seamlessly execute asynchronous code, enabling our applications to perform other tasks while waiting for computations to finish, making code not only cleaner, but also more responsive in real-world scenarios. Now let's see how we can implement concurrent operations using Tokyo's join macro. In this example, we define 2 asynchronous functions, fetchData1 and fetchData2, each simulating requests to different endpoints. The fetchData1 function features an awaited delay of 1 second before returning data, while fetchData2 has a longer delay of 2 seconds. This structure illustrates how we can perform tasks asynchronously without blocking, enabling both functions to run concurrently. Next, we'll utilize Tokyo join within our main asynchronous function by calling join with both fetchData1 and fetchData2. We trigger both operations to execute simultaneously. The macro awaits both futures, and when they complete, it returns a tuple containing the results from both functions in a single operation. This efficient handling significantly reduces total waiting time, allowing our application to process these operations in just over 2 seconds instead of the 3 seconds it would take if processed sequentially. Finally, we print the results. demonstrating how we can maximize throughput and responsiveness in asynchronous applications. Now let's see how we can implement error handling in our asynchronous code. The function fetchWithError is defined as an asynchronous function that returns a result string. This indicates that it may either produce a successful string result or return a string error message. Inside the function, we simulate a network error by immediately returning an error variant of the result. Next, in our main function using the Tokyo main attribute, we set up the asynchronous runtime. We then call fetchWithError, await, which allows us to wait for the result of the asynchronous operation. The match statement is employed to handle the outcome gracefully. For a successful result, the data is printed, while if an error occurs, it outputs the error message. This approach not only prevents panics but also enables the caller to manage different outcomes effectively. This method exemplifies robust error management in asynchronous scenarios, ensuring that the flow of your application remains smooth and controlled even in the face of potential issues. Now let's take a look at a practical example demonstrating the use of an async block within our asynchronous main function. In this scenario, we begin by declaring the main function as asynchronous with the Tokyo main attribute, which sets up the Tokyo runtime needed for executing asynchronous code. Next, we create an async block encapsulating operations that we want to run asynchronously. Inside this block, we use the Tokyo time sleep function to simulate a delay representing an asynchronous task that takes 1 second to complete. This allows our program to remain responsive while waiting for the operation to finish. After the sleep duration, we return a string, data from async block. Following the async block's definition, we use the await keyword to pause the main function until the async block completes its execution. The result is then stored in a variable, which we print out to the console. This approach illustrates how we can embed asynchronous behavior inline, making it a practical solution for scenarios where offloading tasks to separate functions might be unnecessary. As we navigate through these examples, it's clear that Rust's async await model greatly enhances our ability to write efficient and scalable applications without the traditional callback hell associated with asynchronous programming. One common pitfall is forgetting to use await when calling an async function. If you neglect it, instead of getting the result, you receive the future itself. You don't want your functions to return futures when you're expecting values. Furthermore, we must be mindful of lifetimes and borrowing when working with async code, as using references inside async blocks can lead to complex lifetime issues. In many cases, utilizing own data like string or arc is a practical approach. Now let's discuss how async await coordinates work with other concurrency patterns we've touched upon, like fibers. While fibers allow us to break down execution into preemptive concurrency, futures and async await give us cooperative concurrency. This means that while a fiber may yield control, an async function effectively tells the runtime what to do next when it is ready to proceed, resulting in a power surge of concurrent processes. By understanding how these paradigms fit into Rust's ecosystem, we can make more informed decisions about which approach to use depending on the problem we're trying to solve. For example, while fibers may be beneficial for CPU-bound tasks that require regular yielding, async await shines in I/O-bound scenarios like web servers, where maintainability and readability are high priorities. Before we conclude, let's briefly touch on performance. The overhead associated with using async await is minimal compared to traditional threading models. Particularly in the realm of I/O operations, where tasks spend considerable time waiting, async await shines as it allows the application to remain responsive and efficient without incurring the cost of thread management. Future optimizations and custom executor architectures can further enhance this performance. In conclusion, diving into async and await opens a wealth of opportunities for building advanced applications in Rust. You now have the knowledge to create efficient, synchronous programs that can scale without losing readability or control. Your journey into Rust's concurrency model is taking a significant leap as you explore these advanced patterns. Embrace the power of futures and async await, and watch your applications soar with a newfound ability to handle complexity with grace. Happy coding! Let's dive into Rust Futures, a powerful feature in the Rust programming language that enables you to write asynchronous code in a way that is both efficient and easy to read. To kick things off, we've briefly covered the transition to futures and async await in Rust programming. These tools are essential for writing asynchronous code that is both readable and maintainable. Now, we will talk about futures and their critical role in Rust's concurrency model. Now let's take a look at how we can implement a simple future in Rust using the standard library. We start by importing the necessary components, including the future trait and types for managing context and polling, which will allow us to create our own future called delayed value. This struct does not hold any data. Instead, it defines a method to conform to the future trait. The key part of our future is the poll method, where we determine if the future's value is ready to be used. In this implementation, we simulate a computation that is immediately ready by returning poll, ready 42. The value 42 will represent our output, demonstrating how futures can manage values that are not available yet but can be computed eventually. In the main function, we instantiate our delayed value future and execute it using futures, executor, block on. This function runs the future to completion, allowing us to retrieve the result and print it. This simple setup exemplifies how futures enable asynchronous programming by allowing us to create non-blocking operations, ultimately helping to keep our code clean and understandable while managing values that may only be ready at a later time. Now let's see how we can implement a non-leaf future in Rust using asynchronous I/O operations. The code begins by bringing in the necessary Tokio libraries for networking and I/O tasks. We define an asynchronous function called sendMessage, which encapsulates the steps for sending a message over a TCP stream. Inside this function, we first establish a connection to a TCP endpoint located at 127.0.0.1.8080 using the TCP stream connect method. This operation is awaited, meaning that the function pauses here until the connection is successfully established. Once the connection is ready, we proceed to send a message using the streamWriteAll method. The message "Hello World" is sent as a byte array, and again we await its completion. The use of await here is crucial. It allows the runtime to manage other tasks while waiting for the I/O operation to complete. Finally, we print a confirmation message to the console indicating that the message was successfully sent. In the main function, we create a future by calling sendMessage and use the Tokio runtime to block on this future until it finishes executing. This demonstrates how non-leaf futures can effectively manage asynchronous tasks in Rust, allowing for efficient concurrency. Understanding the role of runtimes is crucial in working with futures in Rust. Unlike other programming languages like JavaScript or C#, Rust does not come with a default runtime for managing concurrency. Instead, you need to install and use libraries like Tokio or Async, which provide the necessary functionality to drive futures to completion. The architecture of a typical async runtime in Rust can be broken down into three main parts: an executor, a reactor, and the futures themselves. The executor is responsible for scheduling and running futures. When a future is polled, it will notify the reactor about I/O events, which then wakes up the future when the event occurs. Here's a simplified view of this interaction. 1. The executor polls a future and receives either poll, ready, indicating that the future has completed, or poll, pending, indicating that it still needs more time or resources to proceed. 2. If it's pending, a reactor monitors the associated I/O source, waiting for the conditions that will allow the future to continue. 3. Once the awaited condition is met, the reactor wakes the future and additional progress can be made. This interaction between the three components showcases the efficiency and responsiveness offered by Rust's concurrency model, allowing developers to build robust asynchronous applications. Now let's see how we can implement a solution for handling CPU-intensive tasks in an asynchronous context using Rust futures. In our example, we define an asynchronous function called processData, which accepts a vector of bytes as input. This function utilizes a feature from the Tokio runtime known as spawn blocking. By using spawn blocking, we can offload potentially blocking computations to a separate thread, ensuring that our main executor remains free to handle other awaiting tasks. Inside spawn blocking, we provide a closure that performs the CPU-intensive operation, here represented by doubling each byte in the input data. This is crucial for maintaining the responsiveness of our application. While the computation occurs, the executor can continue polling other futures. The result of this computation is awaited, and once the operation is complete, we unwrap the result and print it. This approach exemplifies how to balance heavy computations and non-blocking I/O effectively, leveraging the strengths of Rust's async model. By following this pattern, we can optimize performance and responsiveness in our applications. Lastly, as we wrap up this discussion, it's important to recognize the advantages that Rust futures provide. Compared to traditional thread-based concurrency, futures offer several notable benefits. 1. Memory efficiency. Futures are stackless, meaning they use minimal memory overhead compared to stackful coroutines. This is especially crucial for high-performance applications where resource management is a priority. 2. Flexibility. Since Rust allows you to choose your runtime, you can pick one that suits your application's needs best, enabling you to tailor performance characteristics according to your specific use case. 3. Error handling ***. Rust's futures integrate seamlessly with its error handling model, whereby you can effectively manage errors that occur during asynchronous operations, ensuring robustness in your applications. For composability, futures allow easy composition, enabling you to build complex workflows by combining simple asynchronous tasks. In summary, exploring Rust futures gives you a powerful tool for writing efficient, concurrent applications. By leveraging the async await syntax alongside well-structured runtimes, you can harness the full potential of Rust's capabilities to handle both I/O and computational tasks seamlessly. As we continue on this journey, we'll delve into more intricate aspects of futures and their practical implementations in real-world applications. Keep your coding hat on because the world of Rust futures is just getting started. When diving into the world of Rust futures, understanding the distinction between leaf and non-leaf futures is crucial. It's this understanding that enables us to write more efficient and organized asynchronous code. Today we'll explore these two categories, their characteristics, and how we can utilize them in our projects. So far we've learned about Rust futures and their role in asynchronous programming, their classifications, and the architecture of async runtimes. Now we will cover the specifics of leaf and non-leaf futures, their implications, and how they function in Rust. Now let's see how we can implement a simple leaf future in Rust. Here we create a structure called immediate future, which implements the future trait from the Rust standard library. The key feature of a leaf future is its simplicity. When we call the poll method on our future, it immediately returns a poll ready state, indicating that the result is available without needing to wait for any other futures. In this case, the output is the integer value 42, symbolizing that the computation is ready at once. In the main function, we instantiate our immediate future and execute it using the futures executor block on function. This function blocks the current thread until the future completes, ultimately retrieving the result and allowing us to print it to the console. This example succinctly demonstrates how leaf futures operate independently, providing immediate results, which is particularly useful for straightforward tasks where waiting is unnecessary. Understanding this basic implementation lays the groundwork for appreciating more complex asynchronous operations in Rust. Now let's see how we can implement a non-leaf future using Rust's asynchronous capabilities. In this example, we start by defining a fetchData function as a leaf future, which simulates a 1-second delay before returning the value 42. This function operates independently without depending on any other futures, allowing it to complete its task quickly. Next, we introduce the computeResult function, which takes an integer input and simply doubles it. The processData function is where the magic happens as it acts as a non-leaf future. Here we first call fetchData, awaiting its result. Once fetchData completes, the result is passed to computeResult, which is also awaited. This demonstrates how non-leaf futures manage dependencies by awaiting the completion of leaf futures to finalize their own processing. Finally, in the main function, we utilize the asynchronous runtime provided by Tokio to execute processData. The result is eagerly awaited and printed to the console. This entire workflow elegantly showcases how non-leaf futures can orchestrate multiple independent futures to produce a final outcome, contributing to more complex asynchronous programming patterns in Rust. The contrasting behaviors of leaf and non-leaf futures provide us with flexibility in our programming. By understanding how to utilize them effectively, we can build both robust and efficient asynchronous applications. Leaf futures are great for straightforward asynchronous tasks, while non-leaf futures let us build intricate workflows with task dependencies. In larger applications, you might have chains of non-leaf futures that create complex interactions, enabling sophisticated data handling scenarios. When using non-leaf futures, there are several best practices to keep in mind. First, you should always be conscious of how early or late you are awaiting futures. Waiting too late might lead to unpredictable latencies, particularly if you can chain together awaiting tasks early in their execution pathways. Second, keeping your futures loosely coupled can further ease maintenance and scalability. That means allowing leaf futures to operate somewhat independently from their non-leaf counterparts, ensuring they function even as proposed changes are made. Now let's see how we can implement a workflow that aggregates data from multiple sensor streams using both leaf and non-leaf futures. We begin with the fetch sensor data function, which acts as a leaf future. This function simulates a data fetch for a given sensor ID, introducing a 1-second asynchronous delay to mimic real-world date retrieval scenarios. After the delay, it returns a value calculated from the sensor ID, allowing us to represent sensor data flexibly. Following this, we will look at the aggregate data function, which is a non-leaf future. This function accepts a vector of sensor IDs and creates an iterator of futures using the fetch sensor data function. By utilizing join-all, it allows us to await the completion of all sensor data fetch operations concurrently. This method not only enhances efficiency, but also ensures each leaf future operates independently without affecting others. Finally, in the main function, we initiate our sensor IDs, invoke aggregate data, and await the aggregated results. This structure encapsulates the essence of our discussion on loosely coupling futures, meaning each sensor fetch task functions autonomously, contributing to a more organized asynchronous workflow. As we work with both types of futures, it is essential to recognize the performance characteristics associated with leaf and non-leaf futures. Leaf futures are generally lightweight, requiring less overhead. When executed, they immediately provide their results, which is why they're perfect for tasks where interactions with external systems are minimal or managed separately. In contrast, non-leaf futures can introduce overhead because they manage state and control flow based on the outcomes of other futures. This overhead can be beneficial or detrimental, depending on how you structure your asynchronous workflows. By relying on futures effectively, we can run into challenges that help us improve our coding practices. For instance, debugging non-leaf futures might occasionally be complex due to the interconnected nature of their dependencies. This is why proper error handling is vital. Make sure to implement error handling throughout your futures to ensure that when something goes wrong, you can trace the issue back to where the failure occurred, simplifying your debugging process. To wrap up our exploration of leaf and non-leaf futures, let's consolidate what we've learned. We initially defined leaf futures as those asynchronous operations that don't wait for others to complete, allowing straightforward execution paths. Non-leaf futures, however, demonstrate a more complex orchestration of tasks where multiple futures may depend on one another. We explored several examples, from basic implementations to more complex aggregations involving sensor data. We also touched on best practices for keeping your futures loosely coupled and managing performance efficiently. As you dive deeper into Rust and its asynchronous capabilities, remember that understanding the intricacies between these two types of futures will empower you to create more efficient and maintainable code. Whether you're designing simple tasks or complex workflows, these principles will serve you well in your programming adventures. Keep experimenting with futures in Rust, and the more you practice, the easier it will become to manage these asynchronous operations effortlessly. Happy coding! A fully functional async runtime is the backbone of any asynchronous system in Rust, making it capable of handling I/O operations efficiently. In this lesson, we will dive into the essential components that comprise an async runtime, specifically focusing on the reactor, executor, and future. So far, we learned about leaf and non-leaf futures in Rust asynchronous programming, highlighting their differences and practical applications. Leaf futures represent independent asynchronous operations, while non-leaf futures depend on the outcomes of other futures, enabling complex workflows. We discussed examples demonstrating how to utilize both types effectively, as well as best practices for keeping futures loosely coupled and managing performance. Understanding these concepts will help build efficient and maintainable asynchronous applications. Now we will talk about building an async runtime, breaking down its components and functionality. Now let's see how we can implement a basic reactor using the Mio crate to manage incoming TCP connections asynchronously. We begin by specifying the necessary dependencies in our cargo toml file, ensuring that the Mio library is included. In our main function, we define a socket address 127.0.0.1.8080 and set up a TCP listener that binds to this address. This listener allows our program to accept incoming connections. Next, we initialize a poll structure, which is crucial for monitoring events. By registering our listener with the poll instance, we specify that we want to be notified when there are readable events, indicating that a connection attempt has been made. Inside the loop, we continuously call poll to listen for these events. When an event is detected, we accept the socket connection and retrieve the client's address, which we then print. This setup illustrates how the reactor allows our application to respond to incoming requests without blocking execution, facilitating efficient asynchronous I/O handling. The program can continue monitoring for connections while simultaneously processing incoming requests, demonstrating the power of the asynchronous model in Rust. Now let's see how we can implement a basic executor in Rust that will manage the execution of futures. In our implementation, we define a simple executor struct, which contains a run method responsible for driving an async function to completion. Inside this method, we first pin the provided future using a box, allowing us to safely store it on the heap. The car of the executor is a loop that continues polling the future until it's ready to yield a result. For each iteration, a waker is created, which will notify the task when it can be resumed. Here we construct a context from the waker, allowing the future to be polled properly. Depending on the polling outcome, if the future is ready, the loop breaks. If it is still pending, the executor simply continues polling until progress is made. We also define a simple async function, say hello, which prints a greeting when called. By calling the run method on our executor and passing it our async function, we effectively demonstrate how to execute an asynchronous task to completion, providing a foundational understanding of the executor component within the Rust async runtime. Now let's implement a simple custom future that simulates a long-running computation. We start by creating a struct called computation future that takes a duration parameter to specify how long the computation should take. The key aspect of our future is the implementation of the poll method, which is called by the executor to check the readiness of the computation. Inside poll, we first check if the delay has expired. If it has, we use poll ready to indicate that the result is available immediately. However, if the delay is still active, we create a waker that will notify us when the computation can proceed. This is achieved by spawning an asynchronous task with Tokyo spawn, which executes after the specified delay using the sleep function. It's important to note that this design allows other tasks to run while we wait for the delay to complete. Finally, we define the async main function where we create an instance of our computation future with a 2-second delay, await its result, and print it out. This structure allows us to see how futures, when polled, can yield control back to the executor, providing a non-blocking way to handle long-running tasks in an asynchronous context. Now let's implement a basic TCP server that demonstrates how to effectively use the reactor, executor, and futures together in our asynchronous runtime. In this setup, we begin by establishing a TCP listener bound to a specific address, allowing it to accept incoming connections. We create a poll instance to monitor the listener for readable events, indicating that there's data to be processed. As the server operates in a loop, it polls for events and handles incoming connections by accepting them and storing them as tasks in a hash map. Each task simulates a workload that contains a delay, allowing us to emulate processing time for each request. The poll method is used here to iterate through tasks and determine which ones are ready for execution or need to be deferred. By using a future implementation for our tasks, we are able to manage their state within the poll context. When a task is ready, it will print the processed request address. This cooperative multitasking model ensures high concurrency, making your server responsive while efficiently managing multiple connections without blocking, creating a robust asynchronous application. In conclusion, building an asynchronous runtime in Rust involves intricately linking the reactor, executor, and futures to create a system capable of efficient I/O operations. The reactor watches for pending I/O events, the executor coordinates task execution, and futures represent ongoing operations. By mastering these components, you can create performant and maintainable asynchronous applications. Understanding how these pieces interact sets the foundation for implementing robust async systems. As you progress in your journey with Rust's asynchronous programming model, you'll unlock the ability to write code that scales elegantly in complex scenarios. Harness this knowledge, explore more use cases, and continue experimenting with building your async runtimes. Happy coding! Now that you've reached an exciting point, we're delving into the fascinating world of coroutines. In this segment, we will unravel the intricacies of stackless coroutines and discuss how they provide a robust mechanism for modeling asynchronous operations. So far, we learned about the foundational components of an async runtime in Rust: the reactor, executor, and futures. We explored how the reactor monitors I/O events, how the executor manages the execution of futures, and how futures represent ongoing computations. Additionally, we discussed their interactions and implemented examples that demonstrate their roles in handling asynchronous tasks efficiently. This understanding prepares us to build scalable and maintainable asynchronous applications in Rust. Now, we will cover coroutines, starting with what they are and how they allow us to write code that can be paused and resumed, making it much easier to handle asynchronous programming efficiently. Now let's take a look at how we can create a basic structure for our coroutine in Rust. We start by defining a coroutine struct that holds the current state of the coroutine, which is defined by an enum called state. The state enum captures the different phases that our coroutine can be in. It can start, wait for the first future operation, wait for the second future operation, or become resolved after completing the tasks. Next, we provide an implementation for the coroutine struct. Inside this implementation, we create a new function that initializes the coroutine in the start state. This sets the stage for our coroutine to begin executing. By keeping the state management separate in the enum, we can clearly define transitions between different states in the coroutine's lifecycle. This approach allows us to handle the flow of operations efficiently, making it easier to pause and resume tasks as needed, which is critical for writing responsive applications. The design establishes a framework for managing asynchronous operations without the need for complex thread handling, setting the foundation for more advanced features we will implement next. Now let's implement the main functionality of our coroutine using the future trait. In this section, we define how our coroutine will transition through different states based on the responses it receives from asynchronous HTTP calls. The poll method is where the logic unfolds. It runs a loop that checks the current state of the coroutine. Initially, when the state is start, a message is printed to indicate the coroutine is starting, and it sets up the first asynchronous HTTP call by creating a box of the future from HTTP get. This sets the state to wait1, indicating that the coroutine is now poised to receive the response from the first request. As the poll continues when the state is wait1, it checks if the future is ready. If a response is received, the coroutine proceeds to print it out and creates another future for the second HTTP call, transitioning the state to wait2. Once the second response is obtained while the state is wait2, it prints the second response and changes the state to resolved, signaling the end of its operations before breaking out of the loop. The design effectively manages control flow, showcasing the power of state machines in handling asynchronous tasks. Now let's implement an asynchronous function using Rust's async/await syntax to illustrate how we can streamline asynchronous operations. In this example, we create a function called asyncmain. Within this function, we start by printing a message to indicate that the coroutine has started. Next, we perform an asynchronous HTTP GET request to fetch data from a specified endpoint, using the await keyword to pause execution until the response is received. Once the first response is obtained, it is printed to the console, showcasing the result. Following this, we make another asynchronous HTTP GET request to a different endpoint, again using await to wait for the second response before printing its content. This pattern helps in managing multiple asynchronous calls in a clean and readable manner, allowing us to write code that closely resembles synchronous functions while still maintaining the benefits of non-blocking execution. Ultimately, the Rust compiler handles the complexities of state management and function polling in the background, transforming our asyncmain function into an efficient state machine. Now let's see how we can implement our asynchronous function within an executor. In the code, we start with a main function where we declare our asynchronous function called asyncmain. By executing this function, we create a future, which represents the ongoing computation that will eventually yield a result. We then set up a new executor instance, which is responsible for running our future. This executor is a crucial component of the async runtime. It polls the state machine generated by the Rust compiler from our async function. The executor's role is to manage the execution of futures, ensuring they are processed until they complete. To do this, we invoke the run method on the executor, passing in our future. This method orchestrates the polling of the future, allowing other tasks to continue running while waiting for any asynchronous operations to finish. This structure elegantly demonstrates how Rust's async features enable an efficient, non-blocking model of execution, relying on the cooperative multitasking nature of coroutines to optimize resource usage in applications. So do we always have to use coroutines? Not at all. You can choose to use traditional synchronous functions when performance constraints allow. But when it comes to I/O-bound or heavily multithreaded applications, coroutines shine bright, enabling you to handle tasks concurrently without worrying about threads management directly. Do remember that understanding how the underlying system works will empower you to craft better applications. Delve deeper into coroutines, experiment with the async syntax, and build upon the foundation you now have. Happy coding in Rust. Now that we've covered what coroutines are, we can start looking at what they look like in code. Today we're diving deep into the world of handcrafted futures in Rust. This is both a fascinating and practical topic, fundamental to understanding how we can manage synchronous operations efficiently. So far we've learned about coroutines in Rust, focusing on their structure and management, and now we will talk about how to create our own futures from scratch. To kick things off, let's define what a future is. In Rust, a future is a trait that represents a value that may not be immediately available but will be resolved at some point in the future. The beauty of futures lies in their ability to abstractly encapsulate the logic to awaken and produce a result. In essence, futures allow you to write efficient asynchronous programs without blocking the entire application's flow. Now let's implement a straightforward executor to manage our custom future. We define a struct called simpleExecutor that includes a method run which will take our future as a parameter. The generic type f must implement the future trait with an output type of string. In this method, we create a pinned version of our future to safely call the poll method. Next, we enter a loop where we constantly poll our future. To do this, we utilize a waker, even though we don't need it to wake anything in this basic scenario. As we poll, we evaluate the result. If the future is ready, we print the resolved value and exit the loop. If it's still pending, we indicate this with a printed message, allowing for insight into the state of our future throughout its life cycle. This simple executor setup is crucial as it highlights how futures are polled to make progress and obtain results, showcasing the non-blocking nature of asynchronous programming in Rust. Now let's implement a simple executor that will help us manage the polling of our custom future. The simpleExecutor struct serves as the foundation for this executor. It features a method called run, which takes a future as input and drives its progression. The input future must implement the future trait and yield a string when resolved. Within the run method, we begin by pinning the future to ensure that it is safely managed in memory. This is vital because futures may need to be moved as they are polled. A loop is initiated to handle the polling process. In each iteration, a no-op-waker reference is created, and a polling context is established from it, which doesn't require waking any other tasks. Then we call the poll method on the future, checking its status. If the poll indicates poll ready, we print the resolved value to the console. This shows that the future has successfully completed its task. If it returns poll pending, we log a message indicating that the future is still pending, and the loop continues to poll until resolution occurs. This straightforward polling mechanism illustrates how futures can be managed efficiently with an executor. Now that we've constructed our custom future, it's time to see how we can utilize it within an executor to drive its progression. Next, we will write the main function, which acts as our entry point for running the program. In this function, we instantiate our simple executor, followed by creating an instance of myCustomFuture using its new method. The executor's run method is then called with our future as an argument, starting the process of polling the future. It will check the state of the future and print messages indicating whether it is still pending or has resolved. To illustrate how the future can change state after its initial execution, we will directly manipulate the completed field of our myCustomFuture instance by setting it to true, simulating a completion event. After this change, we invoke the executor's run method again with the same future, allowing it to recognize the updated state and print the resolution message accordingly. This approach not only showcases the execution of our custom future, but also emphasizes how futures can be polled and managed effectively within an asynchronous context. Now let's take a look at how we can implement a more realistic future using a struct that handles a delayed task. The delayed future struct is designed to represent a future that will complete after a specified duration. It encapsulates an instant to track when it started, and a duration representing the time it should wait before it's marked as complete. The completed Boolean flag indicates whether the future has finished its execution. In the poll method, we check if the duration has elapsed since the future began. If the current elapsed time equals or exceeds the specified duration, we set the completed flag to true and return poll ready with a success message. This indicates that the operation is completed, allowing any awaiting tasks to proceed. If the duration has not yet elapsed, we return poll, pending, signaling that the future should continue to be polled until it completes. This structure allows us to simulate the behavior of asynchronous operations, showcasing how we can build futures that represent tasks with time delays, an essential concept for managing more complex asynchronous workflows in Rust. Now let's implement the delayed future scenario to further demonstrate asynchronous behavior in our executor. In this code, we set up an instance of our simple executor and create a delayed future with a duration of 3 seconds. This future embodies an operation that simulates a delay before it resolves, showcasing how futures can mimic asynchronous tasks, allowing other operations to proceed without blocking. By calling println to indicate that the delayed future is about to execute, we acknowledge the beginning of the asynchronous operation. When we pass the delayed future to the executor on method, the executor will enter its loop and begin polling the future. Initially, the future will return poll, pending because the set duration has not yet elapsed. After 3 seconds, the future marks itself as completed and yields a result, indicating the operation has finished. This implementation effectively illustrates how futures can manage asynchronous tasks and delays, empowering developers to design responsive applications while adhering to Rust's concurrency principles. While this handcrafted future gives you the flexibility to control its lifecycle, it's important to recognize that building futures manually can become unwieldy as complexity grows. Luckily, the Rust ecosystem offers libraries like Async and Tokyo that provide robust abstractions for handling asynchronous programming. These libraries simplify the creation of futures and allow you to focus more on your application logic rather than the intricacies of the underlying machinery. However, understanding how to create your futures manually grants insight into the core concepts of asynchronous programming, so you can effectively debug or even develop advanced features. Before we wrap up, let's review what we accomplished in this discussion. We kicked things off by defining what a future is and why it's essential for asynchronous operations. Then we built a custom future, showing how to implement the poll method and integrate that with an executor to run our futures. Finally, we also introduced a delayed future example, simulating a real-world scenario. And that's a wrap on futures. You've just learned how to build handcrafted futures in Rust, equipping you with critical knowledge to tackle asynchronous programming challenges effectively. Remember, while it's great to understand the mechanics of futures, leveraging existing libraries to make your life easier as you build more complex systems is often the way to go. Thank you for joining me on this coding journey today. I hope you found this explanation informative and inspiring as you embark on your journey to more sophisticated asynchronous applications in Rust. Happy coding and see you in the next lesson. Now let's implement the fetch URL function to make asynchronous GET requests. This function is marked with the async keyword, allowing it to return a future rather than blocking the execution. Inside, we use request GET to initiate the GET request to the specified URL. Importantly, the function awaits the response, ensuring that our code pauses at this point until the response is available. Once we have the response, we call text await to extract the body content asynchronously, again employing await to handle our future without blocking. The function returns a result string error, which elegantly handles any potential errors that may arise during the request or response retrieval. This structure not only helps in dealing with errors gracefully, but also leverages Rust's powerful type system to improve code safety and reliability. In essence, this method exemplifies how async await simplifies writing non-blocking code while maintaining clarity and ease of understanding. Now let's see how we can implement an asynchronous function to fetch the body of a URL in our HTTP client. We define the function fetchURL, which takes a string slice parameter representing the URL and returns a result type containing either the response body as a string or an error. The function uses the request GET method to initiate a GET request. This method returns a future for the HTTP response. Since we are working in an asynchronous context, we need to await the response with the await syntax. This allows the function to pause and yield control while waiting for the response without blocking other operations. Once we receive the response, we call text await, which again needs to be awaited to extract the body of the response asynchronously. The use of the operator helps us handle errors effortlessly by returning early if an error occurs. Finally, we wrap the body in the OK variant of result, effectively allowing us to pass the fetched content back to the caller. This structure not only promotes better error handling but also aligns with Rust's paradigm of safe and efficient concurrent programming. Now let's see how we can implement our main function to tie all the asynchronous code together. We start by annotating our main function with Tokyo main which sets up the Tokyo runtime, enabling us to run asynchronous code directly. Inside main, we define a string variable URL that holds the URL we wish to fetch data from. We then call our fetch URL function, using the await keyword to pause execution until the response is received. By employing Rust pattern matching, we can elegantly handle the results of the HTTP request. If the fetch is successful, we print the response body, showcasing the data we received. Conversely, if an error occurs, we capture it and output a clear error message. This structure not only maintains readability, but also exemplifies how async await simplifies error handling compared to traditional callback approaches. Overall, this implementation serves as a solid foundation for building our efficient HTTP client, demonstrating the power of asynchronous programming in Rust while keeping the code clean and manageable. Now let's extend our HTTP client to handle POST requests, which allows us to send data to the server. We start by creating an asynchronous function named PostData, which takes a URL and a JSON string as inputs. Inside this function, we instantiate a new request client, enabling us to configure headers and settings for our requests easily. To send the POST request, we utilize the POST method of the client, setting the content type header to applications/JSON to inform the server of the data type being sent. We then attach the JSON body using the body method, ensuring it's converted to a string for proper handling. The send method executes the request asynchronously, and we await its response, capturing any potential errors with the operator. After awaiting the response, we extract the body content asynchronously using text and return it. Next, we will write the updated main function to demonstrate both GET and POST requests, validating that our client effectively manages different types of HTTP calls using async await, thus showcasing its versatility and efficiency in handling various networking tasks. Next, we will implement a function called fetchWithTimeout that aims to enhance our HTTP client by incorporating timeout functionality into our requests. This is crucial for ensuring that our application doesn't hang indefinitely when a remote server fails to respond in a timely manner. In this function, we first create a new instance of request client, which is essential for making HTTP requests. We then issue a GET request to the specified URL using the client's get method. However, what sets this function apart is the use of the timeout method, which allows us to specify a duration, in this case 5 seconds, after which the request will fail if no response is received. This is particularly useful in real-world scenarios when network issues can cause requests to hang. The function then awaits the response and, upon successful receipt, proceeds to extract the response body as text. If the operation succeeds, it returns the body as a result. However, if the timeout occurs or any other error happens, an error will be propagated, giving us the ability to handle it gracefully. This feature significantly boosts the robustness and reliability of our HTTP client. Now let's see how we can implement concurrent HTTP requests by modifying our main function. We start by creating a vector of URLs that we wish to fetch. Each URL is then processed through a mapping function that utilizes our previously defined fetchURL function, generating a collection of futures. This allows each request to run asynchronously, leveraging Rust's powerful concurrency features effectively. Next, we collect all these futures into a vector and use future, join all to await their completion concurrently. This means that instead of blocking the main thread for each request, we can send out multiple requests in parallel. Once all requests are completed, we loop over the results to check for success or errors. Each successful response triggers an output of the response body, while any encountered errors are printed to the standard error stream. This approach not only optimizes the application, making it capable of handling multiple requests efficiently, but also keeps the code clean and easy to understand, consistent with the principles of asynchronous programming in Rust. Now that you have encountered these various aspects of async await and HTTP clients in Rust, let's take a moment to reflect on what we've built. We've examined the structure and implementation of an HTTP client using async await syntax, created GET and POST requests, handled errors, added timeout functionality, and implemented concurrent request handling. This gives us a strong foundation for creating efficient and effective asynchronous applications using Rust. Remember that even though building an HTTP client may seem simple, it serves as a vital building block for applications ranging from web services to microservices and beyond. With async await syntax, you can efficiently manage and scale your applications while maintaining a straightforward coding style. This lesson has not only enlightened you about async await and futures, but it has also prepared you to tackle real-world problems within the Rust environment with confidence. Now you can build upon your newly acquired skills, explore other asynchronous libraries, or even enhance your HTTP client by adding features like request retries, authentication, or custom error handling. The possibilities are endless. Thank you for joining me on this coding journey through implementing async await syntax in Rust. I hope you found this lesson informative and engaging, and that you're excited to put these techniques into practice in your own projects. Happy coding! As you venture into the world of Rust, one crucial aspect you need to master is the concept of runtimes. Runtimes serve as the backbone for driving and scheduling asynchronous tasks, allowing your applications to function smoothly and efficiently. Today, we're diving into the exciting realm of runtimes in Rust, comprehensively exploring what they are, how they work, and why they are essential for building responsive applications. So far, we learned about implementing async await syntax in Rust to create an efficient HTTP client. We covered the setup of necessary dependencies, how to structure asynchronous functions for GET and POST requests, and the importance of error handling and timeouts. Additionally, we explored how to manage multiple requests concurrently using the join macro from the Tokyo library. This foundational knowledge equips us to build robust asynchronous applications in Rust. Now we will talk about runtimes, the essential frameworks that allow you to execute and orchestrate these async functions seamlessly. Runtimes in Rust provide the context required to run asynchronous code. You may be asking, what exactly does that imply? Well, in a nutshell, a runtime is a system that handles task scheduling, execution, and coordination for asynchronous operations. Rust does not come with a built-in runtime. Instead, it allows developers to choose and integrate various libraries as suitable runtimes. The most popular runtimes include Tokyo and Async, each with its own strengths, weaknesses, and use cases. Now let's see how we can implement an asynchronous function using the Tokyo library to fetch data from an API. In this code, we first import the necessary modules from Tokyo and the standard library. The TCP stream connect method establishes a TCP connection to the specified address, in this case, 127.0.0.1.8080, which is a common local endpoint for testing. This call is marked with await, indicating that it will yield control back to the runtime while the connection is being established, allowing other tasks to run concurrently. This non-blocking behavior is crucial for maintaining responsiveness in asynchronous applications. Next, we utilize the write macro to send an HTTP GET request to the API, again using await to pause execution until the write operation completes. The use of after the connection and write calls helps with error handling, automatically returning any encountered errors. Lastly, the function concludes by returning an OK, signaling successful completion of the asynchronous task. This concise structure exemplifies how to harness Rust's async capabilities effectively within the Tokyo runtime, allowing us to build efficient, responsive applications. Now let's implement the main function using the Tokyo runtime. By annotating the main function with the Tokyo main attribute, we designate it as the entry point for our asynchronous operations. This opens the door for us to write asynchronous functions that can be awaited directly within this context, which is a fundamental aspect of Rust's asynchronous programming model. In this function, we introduce the async keyword, indicating that it can execute asynchronously. The return type is defined as EO, result, which allows us to handle potential input-output errors gracefully. Inside the main function, we call our previously defined asynchronous function fetchData. We use await to pause execution until fetchData completes its operation without blocking the entire thread. This non-blocking behavior allows other tasks to be handled while waiting, making our application responsive. Finally, we return OK to signify that the operation was successful, completing our run with the Tokyo runtime in a clean and efficient manner. This setup exemplifies how straightforward it is to harness the power of asynchronous programming in Rust, laying the foundation for building robust applications. Now let's see how we can implement data fetching using the Async runtime in Rust. First, we begin by specifying the Async dependency in our cargo toml file, enabling us to utilize its asynchronous features with minimal configuration. Next, we'll define an asynchronous function called fetchData. Within this function, we establish a TCP connection to a server using TCP stream connect, specifying the address we want to connect to. The use of the await keyword here is crucial, as it allows the function to yield control back to the runtime while waiting for the connection to succeed, enabling the program to remain responsive during this period. After successfully connecting, we send an HTTP GET request to the server using the writeLn macro, which also employs the await keyword to ensure the operation is asynchronous. Once our data fetching operations are defined, we must execute them, which is where the blockOn method of async std task comes into play. To run our async function, we invoke blockOn, which effectively blocks the current thread until fetch data completes, allowing us to handle any potential errors through unwrap seamlessly. This structure reveals how async std provides a straightforward method for managing asynchronous operations, particularly for those familiar with synchronous programming concepts. With both Tokio and async std, task management is streamlined, and you can leverage the runtime to create rich asynchronous applications. A critical aspect of any runtime is how effectively it scales with numerous concurrent tasks. For instance, Tokio uses a work-stealing scheduler, meaning it can efficiently handle long-running or blocked tasks while maintaining performance. This is particularly beneficial when dealing with applications that require a high level of concurrency, such as web servers or concurrent data processing systems. However, as with all tools, the choice between them boils down to your specific use case and personal preference. For lightweight applications, async std may suffice, providing a simple API and familiar paradigms. On the other hand, if you anticipate needing high-performance capabilities and a wider feature set, Tokio is an excellent option. As we wrap up this section on runtimes, it's essential to emphasize the importance of understanding asynchronous programming in Rust. Armed with the knowledge of how to set up and use runtimes like Tokio and async std, you'll find that you can build applications that are not only efficient but also scalable and responsive. Moreover, as you delve deeper into advanced concepts such as task cancellation, error propagation, or using channels for communication between tasks, the runtime's role becomes even more critical. In conclusion, we've covered what runtimes are in Rust, how they facilitate async execution, and the differences between Tokio and async std. By integrating a runtime of your choice, you can harness the full power of asynchronous programming in your applications, ensuring they remain reactive and performant. To put everything we've learned into practice, I encourage you to explore building a mini web server or an asynchronous data scraper. Challenge yourself to integrate multiple asynchronous operations, manage errors, and handle response timeouts. There's a wealth of potential waiting to be unlocked as you explore the full capabilities of Rust's async ecosystem. Remember, each time you call an async function, you're stepping into a world where efficiency meets elegance, and with the right runtime, you're empowered to control the flow and execution of your tasks. The possibilities are boundless and only limited by your imagination. Happy coding! In this lesson, we are diving into the fascinating world of the future trait in Rust. The future trait is a foundational component of asynchronous programming in Rust, enabling us to represent values that may not be immediately available but will be computed sometime in the future. By the end of this session, you'll understand how to implement the future trait and how it integrates with Rust's async ecosystem. So far, we learned about the significance of runtimes in Rust and how they enable the execution of asynchronous tasks. We explored how runtimes like Tokio and async std function, including their setup and basic usage. We also discussed the differences between these runtimes in terms of task management and performance efficiency. This foundational understanding equips us to leverage the power of asynchronous programming effectively in our applications. Now let's delve deeper into the future trait. Now let's take a look at how to implement a custom future in Rust. We begin by defining a struct called myFuture, which serves as a container for any state or init data needed to track the progress of our asynchronous operation. Next, we implement the future trait for our struct, which requires defining the associated output type. In this case, we've specified that our future will eventually yield an i32 value. The core of our future implementation lies in the poll method. This method is pivotal as it determines the readiness of our future. We'll use a pinned reference to self, ensuring safety when dealing with self-referential data. Inside the poll method, we check if the future's computation is complete. If not, we call the executor's wake a method to register that our future is still pending, allowing it to be polled later when it might be ready. If the future is ready, we return poll ready value, where value is the computed result. By using this polling mechanism, we facilitate asynchronous workflows without blocking the thread, allowing other tasks to execute while waiting for our future to resolve. Now let's see how we can implement a custom future in Rust to simulate a delay. We start by defining a struct called delay, which holds two important pieces of information: the time when the delay starts and the duration we want to delay for. This state is essential for the future's functionality, as it needs to track whether the duration has elapsed or not. Next, we implement the future trait for our delay struct. In this implementation, the poll method is crucial. This is what allows the executor to check the readiness of our future. When poll is called, it checks if the elapsed time since start exceeds the specified duration. If the time has passed, it returns poll ready, indicating that the future has completed. If the duration has not yet passed, the method registers a waker, which will notify the executor to poll this future again later, returning poll pending. Finally, we create a new instance of delay using the new method, which initializes the start time and sets the specified duration, allowing us to effectively yield control until the delay completes. This structure and functionality demonstrate how Rust's async programming allows us to delay execution without blocking our main thread. Understanding how to create and manage your futures is crucial, but it's not all there is to it. The future trait is part of a more extensive picture involving wakers and the executor. When a future is polled, if it's not ready, it needs to notify the executor so it can be checked again at a later point in time. That's where wakers come into play. Essentially, a waker is a way to signal the executor that a future should be polled again. Let's consider how we can integrate a waker into our future example. We can utilize Rust's built-in waker type, which is provided through std task waker. When we call cx waker, wake by ref, in our poll method, we signal our executor, letting it know that it should revisit this future because there's a chance, as per its internal state, that it could become ready to yield its value. Imagine weaving a thread between an event loop and the future. Whenever the future determines that it needs more time, it can tell the event loop via that waker, ensuring that no CPU cycles are wasted waiting around. Now let's explore how to set up the Tokyo executor to run our asynchronous code effectively. To do this, first, we need to add a dependency on Tokyo in our cargo toml file, specifying the version and features required for full functionality. This allows our Rust application to utilize the capabilities of the Tokyo runtime, which is crucial for managing asynchronous tasks. Next, we will implement the main asynchronous function of our application. By applying the Tokyo main attribute to our main function, we transform it into an entry point for asynchronous execution. This attribute informs Tokyo to establish the runtime environment necessary for running our futures. Inside the main function, we create a new instance of our custom delay future, designed to simulate a pause in execution for a specified duration. We utilize the await keyword on our delay future to yield control back to the executor, effectively pausing the program until the future is ready. After waiting for 3 seconds, our program prints a confirmation message to the console indicating that the delay has completed successfully. This demonstrates how we can handle asynchronous delays within our application flow. Now let's implement the following example using the joinAll function to concurrently wait for multiple futures to complete. In this code, we first create a vector of delay futures that simulate asynchronous tasks, each representing a delay of different durations. Specifically, we have 3 delays, 2 seconds, 3 seconds, and 1 second respectively. Next, we call the joinAll function, passing in our vector of delays. This function is key, as it allows us to await the completion of all futures within the vector simultaneously rather than waiting for each delay to complete sequentially. By leveraging this approach, we can significantly reduce the total wait time for all operations to finish, illustrating the power of concurrent execution. Finally, once all delays are complete, a message confirming all delays completed is printed to the console. This example not only highlights how to utilize the joinAll function effectively, but it also exemplifies the advantages of asynchronous programming in Rust, enabling us to run potentially time-consuming tasks in parallel, making our applications more efficient and responsive. Now let's take a look at a practical example of chaining asynchronous functions using futures. Here, we define 2 asynchronous functions, task1 and task2. The task1 function simulates a delay of 1 second before returning the value 42. This is achieved using the delay struct we previously discussed, which ensures that the task yields control back to the executor during the waiting period. Next, the task2 function takes the result of task1 as an argument and prints it to the console. The beauty of this structure lies in how we handle these tasks sequentially within the main function. By using await when calling task1, we effectively pause the execution until that task is complete, ensuring that we have the necessary result before proceeding. Once we have the result from task 1, we immediately pass it to task 2, which executes seamlessly. This chaining of functions not only illustrates the composability of futures, but also emphasizes the clarity and conciseness of our asynchronous workflow, allowing us to maintain a clear logical flow in our application. As we wrap up this discussion on the future trait, remember that it is a building block for crafting robust asynchronous applications in Rust. Implementing the future trait empowers you to manage operations that will take time gracefully, allowing you to focus on building rich concurrent applications. Wakers and executors enable seamless integration into the broader Rust Async ecosystem, ensuring that your futures can be efficiently managed and executed. Don't hesitate to experiment with your custom futures and explore their capabilities. The world of asynchronous programming can be complex, but with tools like the future trait, wakers, and executors, you have a powerful arsenal to help you build effective and scalable applications. Happy coding! By now, you also have an idea of how we can achieve both concurrency and parallelism by combining our own runtime with OS threads. Today, we will explore these concepts further, providing a detailed comparison of concurrency and parallelism, their implementations in programming, and how they are essential for maximizing performance in modern applications. So far, we learned about the future trait in Rust, which is essential for asynchronous programming. We explored how to implement custom futures and the role of wakers and executors in managing and executing these futures. Additionally, we discussed running multiple futures concurrently and composing them into complex workflows for improved clarity and reusability. This foundational knowledge primes us for creating robust asynchronous applications. Now we will dive into the intertwined worlds of concurrency and parallelism. Let's start with some definitions. Concurrency is the ability of a system to handle multiple tasks at once by making progress on each task without necessarily running them simultaneously. Think of it as a juggler, mastering the art of throwing and catching balls, where at any point in time multiple balls are in motion but not all at once. On the other hand, parallelism involves executing multiple tasks simultaneously, typically across multiple cores or processes. Picture a team of chefs in a kitchen, each working on their dish at the same time. They are not just managing their time well, they're actually cooking at the same moment. It's essential to understand that while both concepts aim to increase the efficiency of tasks, they cater to different needs and can exist independently or together. A concurrent system can run on a single core CPU by interleaving tasks, while a parallel system requires multiple cores to truly execute tasks simultaneously, thereby improving performance and throughput. Now let's implement a simple example to illustrate concurrency in Rust using the Tokyo runtime. In this example, we define an asynchronous function named performTask, which accepts a task ID. Inside this function, we print a message indicating the task start, simulate a time-consuming operation with a sleep of 2 seconds, and then print a completion message. This structure showcases how asynchronous tasks can perform operations without blocking the main thread. Next, we create the main function, which is also marked as asynchronous using Tokyo main. Here, we construct a vector of tasks we want to execute concurrently by calling performTask with different IDs. We then loop through this vector and spawn each task using Tokyo spawn, allowing them to run independently. To ensure all tasks complete before the program exits, we introduce a sleep call of 3 seconds at the end, illustrating how the main thread can wait while the tasks execute concurrently. This example effectively demonstrates Rust's concurrency model, showing how multiple operations can be managed efficiently without waiting for each one to finish sequentially. Now let's see how we can implement parallelism in our Rust code using the Rayon library. In this example, we start by initializing a large vector of integers, specifically including the numbers from 1 to 100,000, which gives us a substantial dataset to work with. We then utilize Rayon's parIter function to create a parallel iterator. This is a powerful feature that allows us to process each element of our dataset simultaneously across multiple threads, significantly speeding up computations. As we map each element to a new value, we double each integer in the vector. The use of map ensures that the operation takes place on every item efficiently and concurrently, leveraging the capabilities of multi-core processes. Finally, we use the sum method to aggregate all the doubled values into a single total result. This computation not only showcases how to execute operations in parallel, but also effectively illustrates the potential performance benefits when handling large datasets in Rust. The program concludes by printing the total sum, demonstrating the efficiency of parallel operations. Now let's implement a web server that demonstrates both concurrency and parallelism in Rust. This code utilizes the Tokyo runtime to handle multiple HTTP requests concurrently by defining an asynchronous function called handleRequest, which accepts a request ID. Within this function, we simulate processing each request with a print statement. For the computationally intensive part, we employ task spawn blocking, allowing us to offload the heavy lifting to a blocking thread without hindering the main event loop. Here, we create a vector of data and utilize Rayon's parallel iterator to double each element and calculate the sum, effectively executing this operation in parallel across available CPU cores. In the main function, we set up a vector with simulated request IDs, iterating through each ID to spawn concurrent handleRequest tasks. This asynchronous approach handles each request independently without waiting for one to complete before starting the next, thereby maximizing throughput. We conclude by introducing an artificial delay to ensure all requests are processed before the program exits. This implementation perfectly illustrates the hybrid use of concurrency for managing tasks and parallelism for executing intensive computations efficiently. Now let's take a look at how we can safely share mutable state across multiple threads using Rust's powerful concurrency primitives. In this example, we start by creating a counter wrapped in an awk, atomic reference counted, and a mutex, mutual exclusion. The awk allows us to share ownership of the counter between threads, while the mutex ensures that only one thread can access the counter's value at any given time, preventing race conditions. Next, we spawn 10 threads in a loop, each tasked with incrementing the counter. To achieve this, we clone the awk, providing each thread with its own reference to the same counter. Inside the thread, we lock the mutex to gain exclusive access to the counter. Upon obtaining the lock, we safely increment the counter by dereferencing and modifying its value. Finally, we join all threads to ensure they complete their tasks before we access the final value of the counter. By locking the mutex, once more to read the final count and printing it out, we can confirm that each thread successfully incremented the counter. This illustrates how we can leverage Rust's concurrency model to manage shared state safely and effectively, enabling efficient parallel operations. Advancing further, concurrency and parallelism are critical concepts that drastically change how we approach programming. They enable us to design systems that are not only responsive, but also capable of handling demanding computational loads. The essence of managing them lies in correctly utilizing the right tools and libraries in Rust, understanding both the underlying principles and the programming constructs available. As we explore more advanced asynchronous patterns in Rust, remember that mastering concurrency and parallelism allows you to craft applications that can thrive in a world demanding speed and efficiency. You'll be able to improve application performance, offering better user experiences, quicker data processing, and ultimately more reliable systems. In summary, we've covered the fundamental differences and implementations of concurrency and parallelism, explored several examples showcasing these concepts in action, and discussed their respective importance in modern programming. Understanding these will not only enhance your Rust coding capabilities, but also open up new possibilities in your software development journey. Happy coding, and may your threads always be safe. In our journey through the fascinating world of programming, we often encounter constructs that help us manage tasks more effectively. One such construct is the coroutine. Today we're diving into the world of coroutines in Rust, a powerful feature that allows for more readable and maintainable asynchronous code. We'll explore how coroutines behave and how we can improve them by allowing variables to be stored across state changes. This enhancement will enable us to handle more complex applications without messy state management. So far, we learned about concurrency and parallelism in programming, focusing on their definitions and how they manifest in Rust. We explored the future trait for asynchronous programming, illustrating concurrency through custom futures and the Tokyo library. Additionally, we discussed parallelism using the Rayon library for executing tasks simultaneously across multiple threads. This foundational understanding equips us to implement efficient, robust applications leveraging both concepts effectively. Now we will talk about coroutines and how they can be enhanced to improve our programming experience. First, let's clarify what a coroutine is. At its core, a coroutine is a special type of function that can pause its execution and yield control back to the caller, allowing other code to run in the meantime. This is particularly useful in asynchronous programming, where we want to avoid blocking the main thread while waiting for tasks like I/O operations to complete. With Rust's native support for async programming through the future trait, coroutines can aid in writing cleaner, more effective non-blocking code. Now let's take a look at a simple coroutine definition in Rust. The async main coroutine begins by logging a message indicating that the program is starting. It then performs two asynchronous HTTP GET requests using the HTTP GET method, which retrieves data from specified endpoints. Notice how we leverage the wait method to yield execution while waiting for the server's response without blocking the entire thread. This is where the non-blocking nature of asynchronous programming shines. However, it's important to recognize a limitation in this approach. Any local variables defined before a wait call become inaccessible when the coroutine resumes execution. To address this, we need mechanisms for maintaining state across these yield points. By implementing a struct to hold state information, we can ensure that critical variables persist between these asynchronous calls. This allows us to carry context through our coroutine, providing a more robust foundation for managing data flow as we handle the incoming responses, ultimately enabling our coroutines to operate more like traditional functions with retained state. Now let's see how we can implement a simple coroutine in Rust that maintains state across asynchronous calls. We begin by defining a struct named CoroutineState, which holds a counter that tracks the number of responses received during the coroutine's execution. This struct has a default implementation, initializing the counter to 0, thus allowing us to safely manage the state of our coroutine. Next, we create the coroutine0 struct, which incorporates our coroutine state. This encapsulation is crucial as it enables us to manage the state across multiple asynchronous calls without losing track of it. In our async main function, we initiate an instance of coroutine0, indicating the start of our coroutine. The procedure involves making two HTTP GET requests sequentially. After each request, we print the response and increment our counter effectively using Rust option type. This ensures that if the counter is none, it remains safe and does not panic. Finally, we output the total number of responses received, which illustrates how a coroutine can retain state and present meaningful information, showcasing a more manageable approach to asynchronous programming in Rust. Now let's take a look at how we can define different states for our coroutines using enums. Enums in Rust are a powerful feature that allow us to encapsulate the behaviors and associated data of various states effectively. In this case, we define a coroutine state enum that encompasses several potential states our coroutine can be in, such as start, wait1, wait2, and resolved. The wait1 and wait2 variants are particularly interesting, as they include a pin boxed in future output equals string. This means that each of these states can hold a future that when awaited will result in a string. By structuring our coroutine state in this way, we can clearly delineate the progress of our coroutine through different phases of execution while managing the data relevant to each state. This design allows for efficient state transitions and reduces memory usage since each state only contains what is necessary for its operation. Leveraging this enum structure will enable us to build more complex coroutines while maintaining clarity and safety in our program's state management. Now let's take a look at how we manage state using a match construct within our coroutine. In this example, we focus on the wait1 state, where our code first polls a future to check if it's ready to yield a response. The match statement allows us to elegantly handle different outcomes from the polling. If the future is ready, we retrieve the response and print it out, showcasing how we can interact with the data obtained asynchronously. Furthermore, upon successfully receiving the response, we transition to the next state, wait2, by updating our coroutine state. This not only demonstrates the dynamic nature of state management but also highlights the organization that the match construct provides. By using enums to define our states and leveraging the match statement to process them, we maintain clear and efficient control flow in our coroutine. This approach allows us to manage multiple futures while ensuring that the coroutine stays responsive and organized as it processes various states, thereby enhancing our ability to build complex applications effectively. In conclusion, coroutines in Rust, when enhanced with state management capabilities, empower developers to create more complex applications without falling into the traps of messy state handling. By incorporating structs and enums, we harness Rust's strong type system to build robust, maintainable code. We've learned how to store variables across waits and how to structure our coroutines to support that functionality. This is just the beginning. As you get comfortable with these concepts, you can dive deeper into more advanced features like self-referential structs, pinning, and even asynchronous patterns that leverage the Rust async await syntax effectively. Remember, the power of coroutines lies in their ability to allow you to focus on the flow of your program, rather than the intricate details of managing state and execution flow. With these tools in hand, you can create efficient, elegant solutions to complex problems. So roll up your sleeves, experiment with these ideas, and enjoy building your next asynchronous application. Now let's see how we can implement a self-referential struct using Rust's ownership model. In this example, we define a struct called self-referential that contains a string named data and a reference to a string slice, reference, which points to a part of data. However, when we attempt to create an instance of self-referential in the main function, we encounter a problem. We try to initialize reference with a reference to data, but this results in a compile time error because the borrow checker cannot guarantee that reference will remain valid as long as the self-referential instance exists. This highlights one of the core challenges with self-referential structs in Rust, managing the lifetimes of references appropriately to avoid dangling pointers. Next, we will explore how to redefine our approach by incorporating smart pointers like RC and refcell, which will allow us to sidestep the strict ownership rules while still benefiting from the self-referential structure. This will enable us to create more complex relationships between our data and references, leveraging Rust's safety guarantees effectively. Now let's implement the following example to demonstrate the use of RC and refcell in managing self-referential structs. We define a struct called self-referential, which contains a reference-counted pointer to a string wrapped in a refcell, allowing for interior immutability. This design enables multiple instances to own the same data, effectively sidestepping the borrowing issues we faced earlier. In the self-referential implementation, we have a new function that initializes our struct. Inside this function, we create an RC refcell string, allowing us to share mutable string data safely. By cloning this data to set the reference, we ensure our struct maintains a valid but independent snapshot of the string content when created. In the main function, we instantiate the self-referential struct and pass a string to it. Then we proceed to print both the string data from the data field and the reference. This snippet demonstrates how to access the interior data reference by RC while adhering to Rust's strict borrowing rules, showcasing the elegance of our solution to managing self-referential structs effectively. Now let's implement a more complex self-referential struct to illustrate how we can manage relationships between data using smart pointers. Here, we define a linked struct that represents a node in a singly linked list. Each node holds data as a string wrapped in an RC refcell, which allows multiple nodes to share ownership of the same data without violating Rust's strict borrowing rules. The struct has a field called next, which is an option type containing an RC refcell linked struct. This enables each node to potentially reference another node, allowing us to build a chain of linked nodes. The append method adds new nodes to the end of the list. It does this by creating a new node wrapped in RC and refcell, and then setting the next field of the current node to point to this new node. To visualize our linked list, the print method recursively prints the data stored in each node. By borrowing the data, we maintain access to it while still adhering to Rust's borrowing rules. This demonstrates how self-referential structs can elegantly manage complex data relationships while ensuring safety and performance. You may be wondering why we might need to use self-referential structs in real-world applications. One common scenario is in data modeling, where relationships between entities can create natural self-references. Think about scenarios in social network applications, game engines, or even parser implementation that requires tracking states across different contexts. While it might seem complex, self-referential structures help in creating clear, concise representations of such relationships. Another critical aspect of self-referential structs is their use in creating more performant and maintainable code. For instance, by keeping references to own data within the struct rather than duplicating data across several locations, we enhance performance and reduce memory usage. This not only leads to clean data handling, but also significantly cuts down on runtime costs associated with data copying. Now let's implement a finite state machine using self-referential structs in Rust. We begin by defining a state struct that holds two fields, a string representing the name of the state and an optional reference to the next state, encapsulated within an RC pointer. This allows multiple states to share ownership of the next state without compromising memory safety. The state struct includes a constructor method, new, which initializes the state with a specified name and sets the next state to none, indicating that it initially doesn't transition anywhere. We then define the setNext method to establish connections between states, where a state can point to another state by updating its next field with an RC pointer to the intended next state. The transition method is vital in this setup, as it prints the current state's name and recursively invokes the transition on the next state if there is one. In the main function, we create a sequence of states by instantiating state objects and linking them through setNext. This demonstrates how the finite state machine operates seamlessly, transitioning between states and maintaining a clear flow of logic in managing state changes. As we engage deeper with self-referential structs, we encounter scenarios where performance tuning becomes paramount. Consider that every time we try to access data in our structures, it might incur a performance hit due to dynamic borrowing. Particularly with a significant amount of data processing, we want to ensure our designs remain efficient. Careful usage of RC and ref-cell, while beneficial, should be balanced with the need for performance-sensitive applications. Exploring alternatives is critical, such as using box when only single ownership is needed, or employing borrow-checker-friendly designs where applicable. In summation, learning about self-referential structs in Rust enhances your capability to manage complex applications effectively. These structures allow us to build efficient models while upholding Rust's guarantees about memory safety and ownership. By leveraging smart pointers and understanding their behaviors, we can create versatile, self-referential designs while maintaining a clear state and relationship dynamics. If you practice implementing these concepts in your projects, you'll find a wealth of opportunities to create robust and scalable applications. So now we're at the end of our exploration into self-referential structs. You've learned about their definitions, the challenges they present within Rust's unique memory management paradigm, and how we can utilize smart pointers to model complex interactions. With this knowledge in hand, you can confidently tackle the problems presented in your programming journey. Happy coding, and remember to keep experimenting with Rust. Pinning in Rust is a crucial feature for safely handling references in scenarios where the memory address needs to remain constant. Today, we will dive into the concept of pinning, how it works, and when to use it in Rust programming. So far, we learned about self-referential structs in Rust, their significance in managing complex data structures, and the challenges posed by Rust's borrow checker. We explored how to implement these structs using smart pointers like RC and ref-cell to allow for shared ownership and interior mutability. Additionally, we discussed practical examples including linked structures and finite state machines, highlighting the advantages of self-referential designs. Understanding these concepts will enable you to create efficient and safe applications in Rust. Now we will cover the concept of pinning, which plays a significant role in ensuring safe memory management. The essence of pinning in Rust revolves around the idea that some types, particularly those with self-referential structures or internally mutable states, require their memory address to remain stable throughout their lifetime. When you pin a value, you are preventing it from being moved, which is vital because moving it can invalidate any references that point to it. This concept is especially useful when dealing with async programming, where you might have async functions that yield execution, requiring you to maintain a stable state across these yields. The primary type used for pinning in Rust is pin, which you can find in the std pin module. Now let's see how we can create a pin in Rust using a simple struct. We begin by defining a struct named myStruct, which contains a single field value of type i32. In the main function, we first instantiate myStruct with a value of 10. This instance, however, is just a regular struct and can be moved, which is not suitable for scenarios requiring memory stability. To pin our struct and ensure its location in memory remains fixed, we utilize box pin, which wraps our instance in a box, effectively pinning it. By doing this, we guarantee that myStruct cannot be moved in memory. When we need to access the value stored in our pinned instance, we call the asref method, which retrieves a reference to the underlying struct. This approach underscores the significance of the pin type in managing memory more safely and effectively in Rust, particularly in use cases involving self-referential structs or async programming where stability is crucial. Thus, we've explored creating and working with a pinned value, demonstrating the importance of memory management in Rust applications. Now let's see how we can create a self-referential future in Rust by implementing the future trait. We begin by defining a struct called myFuture, which includes a single field value to hold a string. This struct is set to represent an asynchronous computation. In order to properly implement the asynchronous behavior required by the future trait, we need to define the poll method. Inside the poll method, we utilize pin and mut_self as the method's receiver, which ensures that our future cannot be moved and satisfies the pinning rules we discussed earlier. By calling self_getref, we obtain a reference to the underlying struct while maintaining the guarantees provided by pin. The method then prepares to return the output of our future wrapped in a poll enum, specifically returning poll, ready with a clone of the value field. Finally, in the main function, we create an instance of myFuture and use box pin to allocate it on the heap while pinning it in place. This step ensures that the future's memory location remains stable, enabling safe execution of this asynchronous operation without invalid references. Now let's take a look at how to implement a self-referential struct using raw pointers. In this code, we define a struct called Self-Referential, which contains a string and a raw pointer that references this string. The implementation of the struct includes a new function that initializes the struct, creating a raw pointer to the string data passed to it. This demonstrates the concept of self-referential structures, but it's crucial to understand the risks associated with raw pointers in Rust, such as potential undefined behavior if the struct is moved or modified incorrectly. Next, we define a method getReference that allows us to safely dereference the raw pointer. The use of unsafe blocks indicates that we are aware of the potential dangers and are taking responsibility for ensuring memory safety. In the main function, we create an instance of self-referential with a string. Although we can print the reference data, it's important to remember that without proper pinning, this implementation could lead to issues if the self-referential instance were to be moved in memory. This example lays the foundation for understanding how to handle self-referential structs responsibly while also introducing the importance of pinning for memory safety in Rust. Now let's implement the following code to illustrate how we can safely manage the dropping of pinned values in Rust. In this example, we define a struct called myDropStruct that contains a single string field named value. We implement the drop trait for this struct, which provides a custom drop method. This method is called automatically by the Rust compiler when an instance of myDropStruct goes out of scope, allowing us to perform cleanup actions, such as printing a message that indicates the value is being dropped. To demonstrate this, we create an instance of myDropStruct, initializing it with a string. We then wrap this instance in a pin using box pin, ensuring its memory address remains stable. The use of pin guarantees that the value will not be moved during the drop process, thus preventing any potential issues with referenced values. When the pinned value goes out of scope at the end of the function, the custom drop implementation is called, and the message is printed safely. This ensures that we manage memory responsibly, leveraging Rust's ownership and safety guarantees effectively. Now let's see how we can transition from a non-pinned to a pinned state in Rust using the pin API. In the code, we start by defining a simple structure, unpinned struct, which holds an integer value. In the main function, we create an instance of this struct, initializing it with a value of 5. However, to ensure that this value remains at a stable memory location, we need to pin it. Next, we pin the value by wrapping our unpinned struct instance in a box, which is a heap-allocated smart pointer, and then use pin new to create a pinned version of our boxed instance. This step is crucial as it guarantees that the memory address of our data will not change, which is vital for maintaining valid references in scenarios that require stable memory locations. Finally, we demonstrate safe access to the data by printing the pinned value. With this approach, we leverage Rust's safety guarantees to ensure that once pinned, our data can be accessed freely without worrying about invalid references or unwanted moves in memory, reinforcing the advantages of pinning in safe memory management. As you explore the realm of pinning in Rust further, consider how it plays a role in real-world applications. The Async programming model is an excellent example where pinning becomes essential. When writing asynchronous functions, pinning helps maintain stable state, enabling smooth execution transitions. Moreover, understanding pinning allows you to craft libraries and systems that rely on safe, bounded references, offering users critical stability in their work. As you build your Rust applications, experimenting with pin will deepen your understanding of memory safety and data handling in concurrent programming models. So embrace pinning and incorporate it into your Rust toolkit to create reliable, efficient applications that take full advantage of Rust's powerful features. By using pinning correctly, you'll find that you're not just leveraging Rust's ownership model, you're also ensuring smooth and predictable behavior in how your data is managed. In conclusion, pinning transforms how we handle memory stability in Rust. It prevents data from being moved, allowing references to remain valid throughout a program's execution, especially in async environments. As we discussed, using pin, we can guarantee safe access to self-referential structs, futures, and other structures requiring stability in memory locations. By understanding and implementing pinning correctly, you can elevate your Rust programming skills, crafting safer and more effective applications. Keep exploring and pushing the boundaries of what you can achieve with Rust, and soon you will be mastering the art of memory management in asynchronous programming. Happy coding! Asynchronous programming is a programming paradigm that allows multiple tasks to run concurrently without blocking each other. In simpler terms, it allows a program to perform tasks, like reading files or making web requests, without making the user wait for each task to finish before starting the next one. Today we'll dive into the basics of asynchronous programming in Rust, explore its mechanisms, and understand its significance in modern software development. So far we learned about the critical concept of pinning in Rust, which ensures that certain types maintain a stable memory address, particularly for self-referential structs and async programming. We explored how to implement pinning using the pin type, which prevents values from being moved, thus maintaining safe access for references. Additionally, we examined practical examples, including creating pinned values and the importance of properly managing memory through the drop trait. Understanding pinning enables developers to create safe and efficient applications in Rust, particularly in concurrent and asynchronous contexts. Now we will talk about asynchronous programming and its building blocks. Now let's take a look at how we can implement a simple asynchronous function that simulates a long-running task in Rust. The code begins by importing the necessary modules, duration from std, time, which allows us to specify time intervals, and sleep from the Tokyo, time module, which provides the functionality to pause execution asynchronously. Next, we define an asynchronous function named long-running task. Inside this function, we first print a message indicating that the task has started. This output informs users that the operation is in progress. We then make use of the sleep function, passing in a duration of 5 seconds. The key detail here is the use of the await keyword, which tells the Rust runtime to suspend the execution of this function until the sleep duration is over. This allows other asynchronous tasks to execute concurrently. Finally, once the 5 seconds have passed, we print a completion message. This structure effectively demonstrates how to create non-blocking operations, enabling other tasks to run while waiting for the simulated task to complete. Now let's implement a Tokyo runtime in our Rust project to manage asynchronous tasks effectively. First, we need to add Tokyo as a dependency in our cargo toml file, specifying its version and enabling the necessary features to ensure we have access to a full set of Tokyo's capabilities. This setup allows us to leverage the powerful features of the Tokyo runtime, which optimizes task execution and provides efficient handling of I/O operations. Next, we move on to creating the main function for our Rust application. By using the Tokyo main attribute, we initialize the Tokyo runtime, which will handle our asynchronous code. Within the main function, we can now run our asynchronous task, long-running task, using the await keyword. This approach ensures that the execution is non-blocking. Our program can continue to perform other tasks while waiting for long-running task to complete. This design allows for highly responsive applications, as the application can interleave processing other tasks while still managing long-running operations seamlessly. By completing these steps, we prepare our application for efficient concurrent execution with Tokyo. Now let's implement a custom future by defining a struct that adheres to the future trait. We start by importing the necessary modules, specifically pin, context, and poll, alongside the future trait from the futures library. Our struct, myFuture, acts as a placeholder for the asynchronous computation we want to define. Next, we implement the future trait from myFuture. This involves specifying the associated type output, which indicates the type of value that the future will ultimately resolve to, in this case, a string. The crux of our future's functionality lies in the poll method, which the executor repeatedly calls to check the state of the future. In the poll method, we use a pinning reference to ensure the safety of self-referential data. Here we employ the logic to determine if the future is ready. If it is, we return poll, ready, with our result, which is hello world, for demonstration purposes. If it's not ready, we would typically return poll, pending, signaling that the future needs to be polled again later. This setup exemplifies how futures operate, forming a fundamental aspect of asynchronous programming in Rust. Now let's take a look at how we can implement a shared counter using asynchronous tasks. In this example, we begin by importing the necessary modules, particularly awk and mutex, from the std sync module. These modules allow us to safely share mutable data across multiple asynchronous tasks. We then define our main asynchronous function, which creates a new awk mutex i32 initialized to 0. The awk atomic reference counting enables safe sharing of the mutex across multiple threads, while the mutex itself ensures that access to the integer is synchronized between tasks. Next, we initialize a vector to store the handles for our spawn tasks. We use a loop to create 10 individual asynchronous tasks, each time cloning the arc reference for the shared counter. Within each task, we lock the mutex, increment the integer value, and subsequently release the lock once the operation is complete. Finally, we await each task to ensure they finish before proceeding to print the final count. This ensures that all increments are accounted for, demonstrating how to manage shared states safely in an asynchronous Rust program while avoiding race conditions. Now let's take a look at how we can make an asynchronous HTTP GET request using the request library, which simplifies the process of handling network calls in Rust. This code begins by importing the request library, which provides convenient methods for making HTTP requests. We then define our main function with the Tokyo main attribute, indicating that it will run within the Tokyo runtime, allowing us to utilize async capabilities. Inside the main function, we perform the actual HTTP call using request GET, supplying the URL from which we want to fetch data. The await keyword indicates that we are awaiting the response, releasing control back to the Tokyo runtime to allow other tasks to execute until the expected result is obtained. This non-blocking behavior is crucial in asynchronous programming, as it ensures that our application remains responsive. Once we receive the response, we call the text method to extract the response body as a string, again using await to handle the potentially asynchronous operation. Finally, we print the response body to the console. With just a few lines of code, we can efficiently make network calls while focusing on our application's logic without getting bogged down by the underlying complexities of asynchronous operations. In conclusion, asynchronous programming in Rust is a powerful tool for writing efficient and non-blocking applications. Understanding the principles of futures, executors, and the importance of state management in concurrent contexts is crucial. As we embark on deeper explorations of async Rust, we will continue to learn about best practices and patterns that can help streamline our code and make it more effective. As you practice, experiment with different runtimes and libraries and keep an eye on updates in the Rust ecosystem. It's continually evolving, and new abstractions and tools are being introduced regularly. Asynchronous programming might seem daunting at first, but once you get the hang of it, you'll discover a new dimension of Rust's capabilities that can elevate your programming skills to new heights. Enjoy the journey and happy coding. Asynchronous programming in Rust opens up a world of possibilities for building efficient and responsive applications. Today, we'll dive into an exciting topic: building a custom runtime that utilizes Rust's future, trait, wake-up, and the async await paradigm. This will be a relatively easy task for us now that we've covered the essential and more complex aspects of asynchronous programming. So far, we covered how to define asynchronous functions and implement custom futures, and we've explored libraries that can simplify asynchronous I/O operations. Now, we'll cover how to create our custom runtime, allowing us to exercise complete control over how our asynchronous tasks are scheduled and executed. Now let's take a look at our runtime implementation. The runtime structure initializes with a vec-deck that holds our tasks, which allows for efficient insertion and removal, ensuring that our task scheduling can occur seamlessly. Next, we define the new method, which sets up a fresh runtime by creating an empty task queue. This is where our newly defined tasks will be stored for future monitoring and execution. Now let's implement the spawn method, which is critical for adding new tasks to our runtime. By accepting a future as an argument, this method wraps the future in a task object, pinning it safely inside a box. This is especially important for asynchronous tasks to ensure they maintain a stable memory address during execution. The wake-up, initialized to none, allows our tasks to notify the runtime when they're ready to be polled again. Once the task is set up, it gets pushed onto our vec-deck queue, making it ready for execution in our main scheduling loop. With this structure in place, we are poised to handle the scheduling and management of asynchronous tasks effectively. Now let's implement the core functionality of our custom runtime in the run method. This method is responsible for continuously polling tasks until none are left to execute. Inside the loop, we first retrieve a task from the task queue. By using a wake-up, we prepare a context for the polling operation, which helps manage task execution. Next, we attempt to poll the task's future. If the task returns poll ready, it indicates successful completion, prompting us to print a message confirming its success. On the other hand, if we receive poll pending, it means the task hasn't finished yet. In this case, we need to store the task's wake-up in the task structure, which allows it to signal when it's ready to be polled again. This approach effectively manages task scheduling by re-adding the pending task back to the queue for future polling. Additionally, we define a wake struct that implements the wake trait, enabling tasks to notify the runtime when they need to be executed again. This cooperative multitasking mechanism is crucial as it allows various tasks to share control over execution, enhancing performance without blocking the entire runtime. Now let's take a look at how we handle task awakening within our custom runtime. In the implementation of the wake struct, we provide a method called wake. This method is crucial because it manages the process of re-adding a previously paused task back into the runtime queue for polling. When a task is awakened, the wake method accesses the runtime's shared task queue, re-adding the awakened task. This behavior ensures that tasks are not permanently removed from the queue if they are still pending. Instead, they are pushed back into the queue to be polled again when the runtime is ready to process them. Next, we'll implement error handling in our task execution loop. By modifying the run method to return a result, we enable the runtime to gracefully handle potential errors during task execution. This adjustment allows us to trace any errors that occur while tasks are being run, offering better debugging capabilities. The loop still retains its car logic where it polls each task, and based on the result of the polling, decides whether to print a completion message, keep the task pending, or store the waker for future polling. This structured approach ensures robustness in the task handling process, making our runtime more reliable. Next, we will write the example task that our custom runtime will execute. This asynchronous function named example task starts by printing a message indicating that the task is beginning. It then simulates a long-running operation by utilizing the sleep function from the Tokyo library, pausing execution for 2 seconds in an asynchronous manner. The use of await here allows other tasks to run during the sleep period without blocking the entire program. Once the sleep duration is complete, the function prints a message indicating that the task has finished. Now let's see how we can utilize our runtime struct to spawn and run this asynchronous task. In the main function, we first create an instance of runtime using the new method, which initializes our task queue. We then spawn the example task using the spawn method, adding it to our runtime's task list. Finally, we invoke the run method on our runtime, which begins processing tasks in the queue. When executed, we should observe the output reflecting the task's start and completion, affirming that our runtime can handle asynchronous execution properly. Building a custom runtime teaches us the inner workings of asynchronous programming and how vital components like futures, wakers, and task execution are interrelated. By implementing our scheduler, we gain flexibility and control, something that can be critical for applications requiring fine-tuned performance or specific behavior. You can take this foundational runtime and expand it. For example, you might want to add features like prioritization of certain tasks or dynamic task management based on system load. Such extensions can take your custom runtime to new heights and make it capable of handling complex requirements. Now, as we wrap up our exploration of building a custom runtime, I hope you can appreciate the intricacies and power that Rust's Async capabilities provide. By embracing the knowledge gained in this episode, you can craft your high-performance applications utilizing asynchronous programming paradigms effectively. Thank you for joining me as we explored the fascinating world of custom runtime development in Rust. Don't forget to apply what you've learned, experiment, and see where your imagination takes you. Happy coding! As we gaze into the future of asynchronous programming in Rust, we embark on an exciting journey reflecting on both the challenges and advancements that lie ahead. With the rapid evolution of the Rust ecosystem, it is essential to comprehend how these changes will shape the way we write asynchronous code and enhance our application's performance. So far, we learned about building a custom runtime in Rust for asynchronous programming, focusing on essential components like future, waker, and the async await paradigm. We created a structure for managing tasks and implemented a polling mechanism to handle task execution efficiently. Additionally, we enhanced our runtime with error handling and demonstrated its functionality by executing a simple asynchronous task. This exploration emphasizes the flexibility and control provided by a custom runtime in developing high-performance applications. Now we will discuss the future of asynchronous Rust programming, focusing on ecosystem evolution, best practices, and how developers can adapt to these changes. One of the most significant hurdles facing the Rust asynchronous ecosystem today is complexity. Much of the perceived complexity can be traced back to the ecosystem's nature, and how various programmers negotiate and contribute to solving the same problems. In a language as rich and versatile as Rust, with many libraries and frameworks emerging, a general consensus on best practices can be elusive. As we look forward, the key to overcoming this complexity lies in fostering collaboration and standardization in the community. To illustrate, let's consider the different libraries that currently exist within the Rust ecosystem for asynchronous programming. Asynchronous runtime libraries such as Tokio, Async, and Small are all contenders, each offering unique features and patterns for handling asynchronous tasks. While competition can drive innovation, it also introduces fragmentation. When approaching a problem, developers may feel overwhelmed by the choices, lacking a clear direction on what library to use or which patterns to adopt. Now let's see how we can implement two asynchronous tasks using the Tokio library to demonstrate effective task management in Rust. We start with the Tokio main attribute, which marks the entry point of our asynchronous program, allowing us to run asynchronous code seamlessly. Inside the main function, we create two tasks using task spawn, which enables us to run these tasks concurrently. In the first task, we print a message indicating that task 1 has started, then introduce a delay of 2 seconds using sleep. This is an asynchronous operation that won't block the main execution thread, allowing other tasks to run concurrently. After the delay, we print a completion message for task 1. Similarly, for the second task, we print that task 2 has started, followed by a shorter 1-second sleep. This shows how we can efficiently manage multiple tasks with varying execution times. Finally, we use a wait to ensure that our main function waits for both tasks to complete before exiting. This pattern exemplifies how to structure asynchronous operations effectively, reducing complexity for developers and enabling more responsive applications. Now let's see how we can implement a custom error type for our asynchronous operations. We start by defining an enum named myError that encapsulates various types of errors we may encounter during execution. This includes specific failure cases such as task failed, which takes a string message to describe the failure, and a general other variant for any unforeseen errors. Next, we create an asynchronous function, performing task, that returns a result type, where the success case is an empty tuple, and the error case is of our custom myError type. In this function, we simulate a failure by returning an error with the variant task failed, providing a descriptive message. This structured approach to error handling promotes clarity and helps developers manage different error scenarios effectively. Now let's implement the main function, which is marked with Tokio main, to denote that it is an asynchronous entry point. Inside, we call performing task and handle the result using a match statement. If the task succeeds, we print a success message. If it fails, we display the error details. This framework not only makes error management accessible, but also encourages maintainable and resilient asynchronous code. Now let's see how we can implement a simple chat server using Tokio, which will introduce you to networking and task management in asynchronous programming. The code begins by importing the necessary components from Tokio's net module, specifically TCP listener and TCP stream, as well as the prelude to access the async capabilities. In the handle connection function, we handle incoming connections. Here, we print the address of the new connection and initialize a buffer to read incoming data. As we enter a loop inside this function, we use socketread to asynchronously read data into the buffer. If data is received, we process it by printing it out, making use of string from UTF-8 lossy to handle incoming bytes correctly. The loop continues until there are no more bytes to read or an error occurs, in which case we log the error and exit. Next, we define the async main function where a TCP listener is created, binding to a local address. The loop waits for incoming connections and spawns a new task to handle each connection asynchronously. This structure allows multiple connections to be processed concurrently, demonstrating the power of asynchronous programming in Rust with Tokio. Looking ahead, another exciting aspect of asynchronous Rust's future involves better integration with the broader ecosystem, potentially including features like multithreading capabilities and more robust interlanguage support. The rise of WebAssembly WASM has already introduced various opportunities for Rust developers, and we might see asynchronous functionalities that leverage WASM for both client-side and server-side operations. Imagine constructing a web application where certain computations are handled in Rust using asynchronous patterns, allowing the browser to execute quickly while maintaining responsiveness. Such seamless integrations could revolutionize how developers approach asynchronous programming, pushing the envelope on performance and responsiveness. As more projects and frameworks adopt WebAssembly, developers will want to explore hybrid applications, where Rust seamlessly interacts with JavaScript or even other languages. Through this integration, we could see a new set of tools emerge to help streamline creating these hybrid applications, allowing async functions to be transpiled to run in the browser directly. In summary, the future of asynchronous programming in Rust is looking brighter than a supernova with the promise of collaboration, standardization, and a vibrant community. As we embrace the evolution of the ecosystem, we will undoubtedly encounter challenges, but we can address them cooperatively. Emphasizing best practices around task management, error handling, and educational resources will cultivate a richer understanding of asynchronous code within the community. By sharing knowledge and creating better tools, we can ensure that as Rust's async capabilities evolve, they remain approachable, efficient, and powerful. With every line of code we write, we move closer to realizing that vision, transforming both our applications and our ability to harness the full power of Rust's asynchronous programming capabilities. Thank you for joining me on this journey, and I look forward to seeing how each of you applies these insights to your work with asynchronous Rust programming.